Yeah. Okay. Yes, good evening to all. Good evening. Good evening to everyone. Welcome to the session. Yeah. So already 5:34. I'm here already before 5:30 itself, but I am waiting for the students. Yeah, almost all they have joined. Okay. Yeah. Let us start the session. So in the last class, we are discussed about the voltage regulation methods. We started. We have completed characteristics of alternators, right? And also voltage regulation methods we were started. There are four methods, four voltage regulation methods. One is the synchronous impedance method, or it can be called as EMF method. And the second one is MMF method, Rother's ampere turns method, or MMF method. And ZPF method, zero power factor method, or Portier method. And lastly, the American Standard Association methods. Okay, yeah. But and we are completed synchronous impedance method. We are completed synchronous impedance method. So there, what we did, synchronous impedance is measured by drawing the OCC and SCC. ZS is measured. Synchronous impedance is measured graphically. And after measuring the ZS, rest of things are calculations. XS is calculated by knowing ZS, XS is calculated, thereby E calculated, generated EMF is calculated, thereby regulation is calculated. So only we have measured synchronous impedance. Because we know the definition of synchronous impedance is open circuit voltage by short circuit current, EOC by ISC. Right? So with that, of course, we have done both the, that is the synchronous impedance both for saturated value and also unsaturated synchronous impedance we have seen. One we have taken based on the rated short circuit current, another one is based on the rated open circuit voltage. Okay. So of course, both will give they will give more than the actual regulation. They won't give correct results if you take even rated open circuit voltage, rated short circuit current. Reason is we are taking the short circuit current and OCC simultaneously, because under short circuit condition, so there is demagnetizing effect of armature reaction. So therefore there is no saturation. Okay. So any field current you take, that regulation will be more than the actual regulation. Okay. Now, in this class, let us start with the next method. Next method is MMF method, Rother's ampere turns method. Rother's ampere turns method. Yeah. Rother's ampere turns method. MMF method. Second method is Rother's ampere turns method. Ampere turns means AT method, or it is also called MMF method. MMF method. MMF method. So this method has given by Rother's, is the scientist. Ampere turns means MMF method. Okay. See, in this method, the why we are calling MMF method means MMF phasors are taken. Sorry, MMF method. The analysis is based on the MMF phasors are taken. That's the reason this method is called MMF method. And In the last class, we have discussed about synchronous impedance method is called EMF method. Why? Why? Because so we have taken everything in terms of EMF phasor. Leakage reactance drop EMF phasor and armature reaction drop EMF phasor or EMF phasor. Generated EMF also in terms of EMF phasor. The earlier in synchronous impedance method, everything is taken in terms of EMF phasor. But in this method, we are going to take the MMF phasor. MMF phasors are taken. That's the reason this method is called MMF method. And actually, I told drop due to leakage reactance is EMF phenomena. Drop due to leakage reactance is EMF phenomena. Because due to self-flux linkages, leakage reactance means due to self-flux linkages, a self-EMF is induced. And that induced EMF opposes the actual generated EMF. In this conductor, by rotor flux cutting, EMF is induced. E is equal to 4.44 kp kd phi ft. But when load connected, due to flux linkages also, an EMF is induced. But that will be in phase opposition. The actual generated voltage 100 volts say, and due to self-flux linkages minus 10 volts in phase opposition, minus 10 volts. What happened? Net voltage will decrease. The leakage reactance is EMF phenomena, but armature reaction is flux phenomena. Right? So leakage reactance drop can be represented with EMF phasor. Armature reaction drop can be represented with EMF phasor. But in earlier method, what we have taken in synchronous impedance method, everything is taken in terms of EMF phasors. That's the reason it is called EMF method. But in this, just converse of that. Converse means drop due to leakage reactance and drop due to armature reaction. Both are considered with MMF phasor. MMF phasor. And the entire drop is considered with MMF phasors. That's the reason this method is called MMF method. Okay, so let me write that first point. In this method, drop due to armature reaction, drop due to leakage reactance and armature reaction. Drop due to leakage reactance and armature reaction. Armature reaction are considered with the MMF phasors. MMF phasors. MMF phasors. And the entire analysis considered with MMF phasors. That's the reason this method is called. This method is called MMF method. MMF method. Everything is taken in terms of MMF method. But earlier we have taken EMF phasors. Okay. Yeah. And this method requires OCC and SCC. This method requires OCC and SCC, open circuit and short circuit characteristics. Okay. So let us see the open circuit and short circuit characteristics. This is OCC. SCC. Both are drawn on the same graph. Y-axis is common. The field current IF. This is E and ISC. OCC. Yeah, this is OCC and SCC. OCC and SCC. Y-axis is common. Correct? Y-axis means 1 centimeter is equal to some 50 volts. Current 1 centimeter is equal to some 1 ampere say. So both can be drawn. Y-axis is common both for voltage and also current. Two graphs we are drawing on the same. With respect to field current, OCC and SCC. Okay. In this, what we are going to do is measure the field current or MMF. See, the field current required, EOC is equal to V rated. After drawing this, we will measure. This is EOC is equal to V rated. EOC is equal to V rated. This let me call IFM. IFM. Main field current. Main field current. Or FM also you can say. Main field MMF. Main field MMF. So let me take easy understanding purpose field current. Field current vector or MMF vectors also. They can be represented both field current vectors and MMF vector. Okay. See here. Yeah. They can be represented considered with MMF phasors or field current phasors. Please add this field current phasors. Field current phasors. Field current phasors. Because MMF, field current, both are proportional, na? Yes. Current ampere turns. What is ampere turns? Current into number of turns. Number of turns are fixed. That's the reason you can take MMF phasor or field current. Both are same. Proportional. On the graph I am taking IF. That's the reason it is easy to show IFM. So IFM, see what is this? IFM is the main field current required to generate rated voltage under open circuit condition. Similarly, IFA, if you take this is IFA. IFA is the main field current required. IFA is the main field current required to produce rated armature current. ISC is equal to IA rated. IS is equal to IA rated. The main field current required to produce rated armature current under short circuit condition. Okay. So this is IFM. Let me write clearly. IFM or FM you can take. IFM or FM. IFM or you can also take FM is the main field current. The main field current is the main field current or MMF to generate rated voltage under open circuit condition. And similarly, IFA or FESA or FEA, MMF is the main field current. Or MMF to produce rated armature current. Under short circuit condition. So IFM is field current for rated open circuit voltage. IFA is the field current corresponding to the rated short circuit current. So that are measured from the OC test and SC test. The meaning of it is, for more clarity, let me show that. See, so alternator, open circuit condition. This open circuit condition, I want EOC is equal to V rated, say. EOC is equal to V rated. Say for example, it is 400 volts, say 400 volts, say. For that, how much field current is required under open circuit condition? That is IFM. Let me call it is IFM. IFM is the main field current required to produce rated voltage under open circuit condition. And similarly, under short circuit condition, this is under short circuit condition, how much field current is required to produce the rated current? ISC is equal to IA rated. IA rated. Say some 20 amperes, say 20 amperes, say. So this is IFA. This is IFA. IFA is the main field. Both are field currents only, DC currents only. IFM and IFA. So IFM is related to rated open circuit condition. IFA is to produce rated armature current under short circuit condition. Both are measured from OCC and another is from ACC. Fine? Yeah. One important point here to note, under short circuit condition, where that generated EMF is going, when we are giving field current, listen, when we are giving field current to this, it will produce generated EMF. It will generate EMF. It will drive the current, short circuit current. Na? Yes, it will drive the short circuit current. In this, what is V? V0. And when V0 means, as we know, E is equal to V plus IA into ZS. IA into ZS. But under short circuit condition, what is V? V0. Under short circuit condition, V is equal to 0, IA is equal to ISC. IA is equal to ISC. Therefore, what is E? E is equal to ISC into ZS. ISC into ZS. That is equal to ISC into XES. That is equal to ISC into XA. Fine? Yeah. So from this, what you are observing, tell me, E is equal to ISC into ZS means IS into XA, IS into XA. Okay? The generated EMF appears in the form of voltage drop. Under short circuit condition, the generated EMF is in the form of voltage drop. So the field current which is given is there, na? The field current IFA. The field current given IFA under short circuit condition is to generate a voltage to compensate impedance drop. To compensate impedance drop. So for example, see, for example, IA rated, ISC is equal to IA rated, that is equal to 20 amperes, say 20 amperes. And ZS is equal to some 5 amperes, say. ZS is equal to 5 ohms, say. Then what is the drop? E is equal to ISC into ZS. That is 20 into 5 is equal to how much? 100 volts. This 100 volts is the drop. That is itself approximately equal to IA XES. And that is nearly equal to IA into XA. IA into XA. So this voltage is in the form of 100 volts is in the form of drop. Therefore, the field current IFA is the field current to compensate impedance drop. The IFA is the field current to compensate impedance drop. Important point is this IFA, whatever we are giving, that is the field current to generate a voltage to compensate impedance drop. Let me write this. Yeah. The IFA under or the field current under short circuit condition, the field current under short circuit condition under short circuit condition is to generate a voltage, voltage to compensate the impedance drop. To compensate the impedance drop. That is mainly to compensate reactance drop. And mainly armature reaction drop. Armature reaction drop. Fine? Yeah. So therefore, how much extra field current is required? I may ask a question for you. Or in the laboratory. I will give you a new experiment for you. What is the new experiment? One machine is being given for you. I will ask. Measure the extra field current required to compensate the drop of voltage. Measure the extra field current required to compensate the voltage drop. How you can measure? Simply conduct the short circuit test. Short circuit test is conducted. The field current which was given under short circuit condition, right? That field current only to compensate the impedance drop. Okay? Yeah. So that's the reason we are taking short circuit test is conducted to measure the how much extra field current required, how much field current to compensate drop. Okay. Now, see. So in this, IFM is measured. For that you want 400 volts, and ISC is measured to compensate the drop. But we need to find the voltage regulation. To find the voltage regulation, what we have to do? I don't want to find the regulation under no load condition, open circuit condition, or short circuit condition. Actual loaded condition, what to do? Actual loaded condition, the alternator has to be supplied the rated volt and also rated current. See here, under actual loaded condition, this is what I want. See. Yeah. See. First open circuit condition, this is the load. Dear students, concentrate. This is the load. Under open circuit condition, if I have given IFM is equal to some 10 amperes say, I am getting rated voltage. EOC is equal to V rated. How much you are getting? V rated is equal to rated voltage you are getting. How much? 400 volts you are getting. Under open circuit condition, you want 400 volts. Fine. Yeah. Now, then connect the load. When load is connected, load is increased, then armature current will comes into picture. Then voltage will reduce, na? Yes. This voltage will reduce. Why? Due to impedance drop. Mainly due to armature reaction drop. Voltage will reduce. So this voltage will reduce. Some 350 volts say. The voltage is reduced to 350 volts. Why it is reduced? Due to impedance drop. Now, I want to compensate. I want rated voltage 400 volts only. It is a no load or full load, whatever it may be. I want 400 volts. No load condition, 10 amperes are given. I am getting okay, 400. But when load is connected, voltage is reduced due to impedance drop. Again, I want to bring back this to 400 volts. What to do? To compensate the drop, you have to increase the main field current. How much you have to increase? That is measured from short circuit test. So that can be IFA. That is nothing but you have to increase the field current, which is equal to how much? IFA. IFA is equal to some 2 amperes say. So here under short circuit condition to circulate 20 amperes, 2 amperes say IFA. Why I am using IFA, you know, mainly to compensate drop due to armature reaction. FA is there, na? IFA. That is mainly drop is armature reaction. That's the reason IFA I am using. Or in other words, inherently there is leakage reactance drop and every drop. Majority is IFA. So voltage has reduced, na? Yes. When voltage is reduced to 350 volts, again I want to maintain 400 volts. So extra field current has to be given. That is measured from short circuit test. That is IFA. Okay, yes. And when IFA 2 amperes extra increase, again voltage will bring back to 400 volts. Then what is your total field current? Tell me. Therefore, total field current is equal to how much? Total field current is equal to IFT is equal to, you have to add these two. So IFT is equal to, total field current is equal to IFM plus IFA. But they are vector sum. IFM plus IFA, they are the vector sum. Why? Because armature reaction is depends on the power factor. Armature reaction is depends on the power factor. So both will be added vectorially. Don't say it is 10 plus 2 to 12. No. Though both are DC currents, but we have to add vectorially. Let us see how they will be added. They will be added like this. This is IFM. This is IFM. How both will be added? This is IFM. Or you can take FM, does not matter. Some textbooks you can find FM or IFM. This is IFM. This is E vector. This is vertical is E. Flux lags induced EMF by 90 degrees. Na? Yes. This is IFM. And this is IFA. For lagging power factor, I am taking IFA. What is this? This is the power factor angle. This is the power factor angle, or nearly psi is equal to phi psi, power factor angle. So this is IFT, total field current, IFT. IFT, total field current or total MMF. This is for lagging power factor. If you take for lagging power factor. Similarly, for leading power factor, for UPF, this is IFM. IFM magnitude is same. IFM magnitude is same. IFM E. This is for leading power factor. Leading power factor will be taken on leading side. Leading side. Okay. UPF will be taken. So, see, one thing let me do, instead of having still more clarity, I will draw one under other. Just a minute, please bear with me. Yeah, so that you will get more clarity. One under other if I draw. This is IFM. See, this is IFM. IFA for lagging power factor. So this is IFT. IFT. This is E. For lagging power factor. Similarly, for leading power factor, IFM magnitude is same. IFM magnitude is same. IFM. But leading will be taken this side. Or UPF will be taken here. This is UPF. For UPF, this is IFT. IFT. Similarly, for leading power factor, if you take leading power factor, IFM magnitude is same. Leading power factor, IFA will be taken here. This is IFA. This is IFT. 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 It's for UPF, and this is for leading power factor. Leading power factor. So in all the diagrams, right? IFA same, IFM same. Once we have measured from OC tester, IFM is related to rated open circuit voltage, IFA rated short circuit current. Both are constant only. But while you are adding, that must be taken phasor sum, vector sum. Then only you can find IFT is more for lagging power factor. Na? Otherwise, some student will raise a doubt like this. Sir, 10 and 2, 12. Is it same 12 for leading power factor, 12 for lagging power factor? Both are same. Huh? Both currents are not equal. Huh? To maintain the rated voltage, more field current is required for lagging power factor. Over excited. Less field current is required for leading power factor. That's the reason, though IFM is 10 amperes, IFA is 2, you can find IFT is more for lagging power factor. Dear student, IFT is more for lagging power factor, but IFT is less for leading power factor. That's the reason they should be added vectorially. Fine? Yeah. Okay. Now, then after finding IFT, next measure the E naught. How much generated voltage? Measure the E naught. V you want total generated EMF how much? See, after getting this, next step is measure E naught corresponding to measure E naught corresponding to IFT from OCC. You go to the already OCC, SCC we have drawn, na? Yes. IFT, total field current. Therefore, you have to find total generated EMF how much. So measure E naught corresponding to IFT from OCC. Yeah. This is IFT. After adding these two vectorially, I am getting this is IFT. Okay. Yeah. For this IFT, this is the E naught. This is E naught. We are going like this. From here, you know field current, voltage can be measured, na? Yes. X-axis is known, Y-axis can be measured. So this is E naught. And once you know the E naught, regulation is equal to E naught minus V by V. So E naught is measured. Total field current is required. Total generated voltage. E naught is nothing but what? Total generated voltage. If you generate this much E naught, then you will get this is V. Okay. Then what is the regulation? Then regulation is equal to regulation is equal to E naught minus V by V into 100. This is a regulation method. E naught minus V by V into 100. Okay. Yeah. This is a regulation method. Fine. This is very clear. Reverse approach. This is called what? Reverse approach. Dear students, listen to me. What we have done, open circuit condition. I want to generate 400 volts. What is the field current is required? Under that, no drop, nothing. So field current 10 amperes, open circuit condition. Short circuit condition, IFA. I have measured how much field current is required to compensate the drop. Therefore, when load connected drop takes place, no load 10 amperes is sufficient. When load connected drop of voltage takes place, to compensate the drop, how much field current is required? IFA. So both are added. But armature reaction, based on the armature reaction, we are adding the field currents. Okay. Here, see, this is E now. When this is E means what is IA? IA will be this side. This is IA. Armature current will be this side. But for leading power factor, IA this side. IFA is to compensate armature reaction. That's the reason we are taking IFA will be along with IA. It is IFA is related to armature reaction mainly. So IA lags, but IA will be leads. Fine. So that then only it is correct. Yeah. Okay. So if you generate this much voltage, I mean to say, for example, you want 400 volts, na? Then how much voltage you need to generate? You need to generate some 450 volts. If you generate 450 volts, then you can get after all the drops, 400 volts you will get. Right? That E naught we are finding total field current and total generated voltage. This is the regulation. Over. Yeah. Now, but this method gives voltage regulation less than the actual value. This method gives voltage regulation. This method gives the voltage regulation less than the actual value. Less than the actual value. Less than the actual regulation. That's the reason called optimistic method. That's the reason called optimistic method. Optimistic method. Optimistic. Optimistic means good method. Earlier synchronous impedance is pessimistic. Pessimistic means bad method. That was given more than the actual regulation. When regulation is more means poor. But here regulation is less. Good. Regulation is less. Okay. Yeah. Optimistic method. Why reason? Let us see. Reason. Why it is giving the less than the actual regulation. Reason for that. Yeah. Reason is, listen. You taken this now? Okay. Reason, whatever IFA we have taken, this IFA, that is less. IFA, whatever we have, IFA or FEA, MMF you can take. Some textbooks you can find IFA and FEA. Because I am drawing E versus IFA, that's the reason I am taking IFA. Otherwise, you can take FEA, MMF. Both are same, na? Yes, ampere turns. Turns constant. Amperes I am taking. Or you can take multiply with turns, ampere turns. Fine. Let us see reason. This IFA, whatever we have measured, that is not correct. That is wrong. That is less. Actual condition, IFA should be more. IFA should be more. Right? See, why reason? Reason is saturation we have not considered. Saturation is neglected. Listen. This is no load condition. If you want rated voltage, EOC is equal to V rated. EOC is equal to V rated, say 400 volts. Say 400 volts. How much field current we have given? Some 10 amperes we have given. IFM is equal to 10 amperes. Fine. And under short circuit condition, ISC is equal to IA rated. Say 20 amperes. For that, how much field current we have given? Say, for example, that IFA is equal to 2 amperes we have given. Say, all numericals just for understanding purpose I am taking. But under actual loaded condition, both alternator must be loaded, na? So I do not bother about under open circuit condition, short circuit condition. I want to find the regulation under actual loaded condition. So this is the load condition. So under this, see, under load condition, I want rated voltage as well as rated current. Both you require. I want rated voltage, at the same time you have to compensate the drop also. That's the reason we have added both. So that is, if I want 400 volts, okay, for that I have got IFM is equal to 10 amperes. Yeah. And when loaded, load increased, current is increased, but voltage is reduced. Na? Yes. Again, same explanation I am giving. I am not drawing in the same diagram. Otherwise, you will get confused. This is some 350 volts. You are getting how much? 350 volts to say. It is reduced to 350 volts. But again, to bring back that, we have to increase the field current. How much that field current we have taken? 2 amperes. 2 amperes. Fine? Yeah. But listen. Under open circuit condition, dear student, listen. Under open circuit condition, if I have given field current of 10 amperes, this is, you have to concentrate because reasoning is not that easy to understand. Textbook, if you see, highly difficult to understand. But you focus here, I am trying to give. These many diagrams are required to understanding this reason. That's the reason I am drawing. Fine? Yeah, see. IFM is equal to 10 amperes, no? 10 amperes. 10 amperes is given, it is producing the flux of 10 milliwebers, say 10 milliwebers it is producing. 10 milliwebers. But when it is 10 milliwebers is producing, the point is on above knee point, above knee point. Under OCC I have taken, it is above knee point. Little saturate, field poles will little saturate. See here, this is knee point, where you are getting EOC is equal to V rated, that is above knee point. Under actual, the machines will be designed to operate little above knee point. It's not fully saturated, little above knee point for utilization of total magnet, for utilization of total rating. So that V rated itself, the field poles are little saturated. Okay, field poles are little saturated at this point. This is measured separately, OCC measured separately. So rated flux, field poles little saturated. And next what we are doing, we are conducting the SC separately. After completion of this, we are conducting SC separately. Short circuit test. This is IFA is equal to how much? 2 amperes are given. When 2 amperes are given, it is producing the 2 milliwebers, say 2 milliwebers. 2 milliwebers. What for the 2 milliwebers? To compensate the armature reaction. The armature flux is in this direction, say for example, this is phi A. Due to phi A demagnetization, net flux decreasing. That's the reason net voltage decreasing. And to compensate that, I have to produce the equal 2 milliwebers. Phi A also 2 milliwebers, say 2 milliwebers. So to compensate that, what we are doing, 2 milliwebers has to be extra, we have to produce. Okay. But that is measured separately from short circuit test. Open circuit separately we are conducting, short circuit we are conducting separately. But under short circuit condition, field poles are not saturated. Field poles are active because small current is given, it will produce the flux. And that to be armature reaction is demagnetization. Field poles are active. Field poles are active. Now, then coming to the actual condition, actual loaded condition. Now you have to say for this. Tell me for this, I will ask for you. From the same pole, machine same. Machine is same. Machine is same. From the same pole. Listen. I have given here field current. IFM is given 10 amperes. 10 amperes. So it is producing the flux. It is producing the 10 milliwebers. 10 milliwebers it is producing. Okay. Under open circuit condition, it is producing 10 milliwebers, say. Fine. Load is not there. When load is not there, it is producing 10 milliwebers. Fine. 400 volts it is producing. But by that time, field poles are saturated. Little saturated it is. 10 milliwebers at rated flux, saturated. Now, see. Now, load is connected. Load is connected, load adjusted, current is rated, current is coming some 20 amperes, say. But by that time, armature flux will comes into picture. Demagnetizing flux, say. That is 2 milliwebers it is coming. Phi A is equal to 2 milliwebers it is coming. Now, to compensate that armature reaction, I need to produce the 2 milliwebers extra. 2 milliwebers extra from the same pole. To produce 2 milliwebers, tell me, at this position, dear students, this is the main key point. Under short circuit condition, I have given 2 amperes, I am getting 2 milliwebers because here pole is active, Okay. But under actual loaded condition, I need to 10 milliwebers for rated voltage. In addition to that, 10 milliwebers it is saturated. In addition to that, I have get 2 more milliwebers. 2 more milliwebers means is the 2 amperes is sufficient. Under short circuit condition, 2 amperes are given. I am getting 2 milliwebers. But under actual loaded condition, already field poles are saturated. From the same pole, I have get 2 milliwebers means is the 2 amperes is sufficient. Similar to the short circuit condition, here also 2 amperes are sufficient. No, saturated means it required IFA must be some 4 amperes are required. When compared with this, here it is 2 amperes, but it is required more current because already it is saturated. Right? Earlier we are doing OCC separately, SCC separately. Under SC 2 amperes are given, 2 milliwebers, but under actual loaded condition, more field current is required because I want rated flux to generate the rated voltage. In addition to that, extra flux. 2 milliwebers from the saturated pole means more current is required. This is IFA dash, actually more field current. And when more field current means total field current is how much? Now total field current is going to be like this. This is IFM. Yeah, we are coming to the ending. Please bear with this because these regulation methods, they will take its own time. Reasonings are not so easy. But final conclusions you can remember. Then assertion reasoning questions. See, this is IFA. This is IFA. I am getting this is IFT, no? IFT actually. IFT. But under actual loaded condition, it requires IFA dash. More field current is required. IFA dash. When IFA dash means this is IFT dash. This is actual. IFT dash is actual. IFA dash is actual. IFA dash is from actual. This is also actual. But IFA by short circuit test. And when IFT dash is more, E naught dash also will be more. E naught dash also more. Go to the back to the our beginning diagram, right? Yes. See, this is IFT dash, actual. IFT dash. When this is IFT dash means this is E naught. This is E naught dash. This is E naught dash. Actual. Say E naught dash is equal to some 480 volts, say 480 volts. That is E naught dash. E naught dash is more, na? Yes. IFT dash is more, E naught dash is more. Therefore, what is actual regulation? Actual regulation is E naught dash minus V by V. And 480 minus 400 divided by 400 is 20%. Actual regulation 20%. But E naught regulation by this method, E naught minus V by V. The 450 minus 400 divided by 400. That is the regulation by this method. E naught dash is the actual value, but E naught is from this method. So let me write the conclusion. The difference is that one. What is the difference? E naught dash. Yeah. E naught dash is equal to 480, no? Yes. The actual regulation, V is equal to 400 volts, say. 400 volts, say. And what is E naught? E naught is equal to, we have got 450 from the diagram. What is E naught dash? It is 480 volts, 480 volts. Therefore, what is the actual regulation? Regulation by, actual regulation is E naught dash minus V by V into 100. That is equal to how much? 480 minus 400 by 400 into 100. So that is equal to how much? You are getting 20%. Actual regulation 20%. But regulation by MMF method is equal to E naught minus V by V into 100. That is equal to how much? 450 minus 400 divided by 400 into 100. That is equal to how much? 12.5% you will get. 12.5% you will get. So regulation is less now. When compared with this regulation is less compared with actual regulation. So actual regulation is 20%, but the regulation by this method it is 12.5%. Okay. So therefore, it is said to be the same thing I will write here. IFT dash. So IFT dash. IFA dash. IFA dash will be more than the IFA. IFA dash is actual. Therefore, IFT dash is more than the IFT. Therefore, E naught dash is more than the E naught. Now, E naught dash minus V by V. That should be greater than the E naught minus V by V. So, this is regulation. Actual regulation. Regulation actual is more than the regulation by MMF method. Therefore, from this, regulation by MMF method is less than the regulation actual. Right? Regulation actual. So here field current is not sufficient. Field current is less. In other words, saturation is neglected. Dear students, whenever question is coming, say in this, ultimately, last final conclusion is field current under short circuit condition we have measured. Field current to compensate the drop, it is measured from short circuit test. But where under actual loaded condition, field poles little saturate. Therefore, more field current is required. Okay, more field current is required. The saturation is neglected. Taken this? Fine. Right? You can take instead of FEM, IFA you can take, like IFM is there now, you can take with FEM, no problem. IFA with FA, IFT with FT, MMF. Yeah. So final conclusion is, I'm going to write, whenever examination is coming, you remember this final conclusion. Conclusion is like this. In this method, the field current to compensate the field current or MMF to compensate the drop. Is measured from short circuit test, short circuit condition, which is less short circuit condition. But under actual loaded condition, short circuit condition where field poles are active, no saturation, that is no saturation. But under actual loaded condition, the field poles little saturate. Then the field current, to compensate the drop, The field current to compensate the drop, that is IFA. IFA dash should be more than the field current, more than the IFA measured from short circuit, measured from SC condition, Therefore, IFA dash is greater than IFA, IFT dash is greater than IFA dash. Therefore, E naught dash is greater than the E naught. Then regulation actual is more than the regulation by MMF method. Okay, MMF method. In other words, saturation is neglected. In other words, saturation is neglected. Yeah, that's the point. Ultimately, assertion and reasoning type of questions, you won't give this big explanation. Na? Simply, it is nothing but saturation is neglected. Saturation is neglected. Okay? This is a method. Over. Fine? Yeah. And any doubts in this, please, before going to the next method, tell me, any doubts are there? Okay, I hope the other people also may have same doubts. Yeah, just for 5 minutes doubts, and then we will move to the next topic.
Good evening, sir.
Good evening. Yeah, hello.
In a leading case, when we are calculate that from SCC test, that will be again that will be demagnetizing.
Where leading side
we will calculate for leading load.
Okay, leading side. See, leading side 400 volts. You want 400 volts, na? When you want 400 volts means no load condition. IFA given 10 amperes have given.
Yes.
You are getting 400 volts.
Okay.
But when load is connected, its voltage is going to be increased. Leading power factors, magnetization.
Magnet.
It will be more than 400. 450 say. 450 means again you want to maintain what to do?
Again for actual value.
You have to decrease. Right? That is what coming. This is by phasor sum. That's the reason I am taking here. IFT, you see, is it less than in this case? You see, in this case, IFT is less than or not?
IFT because of magnetization. Okay.
That's the reason we have to add vectorially. If you take ZPF lagging, it is totally maximum. ZPF leading, it is exactly opposition. If you take ZPF lagging, how it is going to be? IFA will be, it comes exactly in phase opposition to IFM.
Okay.
That's the reason we have to add vectorially.
Means actual case, it will be more
actual cases, saturation, throughout this saturation, we are not considered because IFA measured from short circuit test.
Yes.
But under actual loaded condition, I want rated voltage plus rated current.
Yes.
So rated voltage means rated flux is there. Machine works at a little saturation condition. Okay. At that time, to compensate armature reaction, more IFA required. IFA we have taken short circuit test, but actually IFA will be under actual loaded conditions. It will be saturated.
Thank you, sir.
Okay, right. Next, anyone? Hello.
Hello, sir. Hello, sir. Good evening, sir.
Good evening. Tell me.
Sir, today's first we said one point called MMF. In MMF method, everything we will go into as MMF parameters.
Yes.
Sir, can you please?
In this, I have taken IFM in place of FEM. You can write FEM. That's the reason I have written there IFM. Yeah. In this, I have used any E vector. E is equal to, in the last class, what we have done. E is equal to square root of V cos phi plus IA RA whole square, V sin phi plus IA XS whole square.
Yes.
No, we have used it there. And the IA axis is nothing but EMF phasor. That E is equal to square root, from where it will come? Vector diagram only, EMF vector. I have not drawn, okay, but it is understood that EMF. But here I have used any such kind of vector. No. Here everything is in terms of MMF. I have taken V, how I have taken, V is taken in terms of IFM or FEM, say, FEM. But how you have taken IA ZS drop, or that is IA XS drop, how we have taken IFA, IFA, FA. Yes.
Okay, sir.
We also taken in terms of phasor, MMF phasor, because you know E is proportional to flux. Flux is proportional to what? Field current. That is proportional to MMF. That's what voltage can be taken in terms of. But E is proportional to V, na? Yes, E proportional.
That means
to
analog is.
analogous. Exactly, analogous.
Okay, sir.
Analogous we are taking. In this MMF phasors we are taking. That's the reason it is MMF method.
Okay, sir. Thank you, sir.
Right. Hello? 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 Anyone? And don't think much on this method. Only you have to remember that reasoning is there, na? In these questions are mainly optimistic method. Why reason? So the reason it is taking more time to explain the reason.
Sir.
Yeah.
Sir, my doubt is, sir, in this, why are we always, we consider that the machine is operating under saturation conditions in actual cases?
Yes, above knee point with, otherwise machines are never be, see, it is not operated at this particular condition. How it is? Because see, this is there, na? This is like this. We never operate below knee point. We never operate below knee point. Below knee point means, are you using this magnetic properties, all magnetic capacity of the machine fully? No. Even if you use here exactly at the knee point, then also not good. But if you use here this portion, don't think this portion is not saturated. Little saturated. Almost this portion also linear. But we never use this portion. No. Normally it will be taken. This is the operating region. Okay. Utilization of magnet. I have to utilize the magnet, na? Full rating.
Okay, sir.
That there also almost linear. And don't think above knee point it is not fully saturated. Not totally non-linear.
It is, it's slightly saturated.
Slightly saturated. But even though slightly saturated, I can use, okay, comfortably I can increase, no problem. Utilization.
And sir, even they also say that if saturation increases, losses also will increase.
That is okay, but how long? On the diagram, you will be feeling it is more a curve you are finding. But above knee point also, it is not much curve, light curve. It's very light, like this, say, like this I am getting. Okay, it's okay, fine, even using on that also.
All right, sir. Thank you, sir.
Right, okay. Now let us go for the next method. Here, students, I am going for the next method. Fine. Yeah. Next method is ZPF method. ZPF method. Okay. Once we are completed this regulation method, say, now our topics will be topic wise. They will be good topics. But these regulation methods, they will take their own time. Right. Next method is ZPF method, zero power factor method. Zero power factor, ZPF method. ZPF method or Pottier method. Pottier is a scientist. He has given this method. Okay. Pottier method. See, in this method, in earlier two methods, what we have done? In earlier two methods, drop due to armature reaction and leakage reactance, both are combinedly considered as either EMF factor or MMF factor. In synchronous impedance method, both are taken as EMF phasors. But MMF method, both are taken as MMF phasors. Strictly speaking, as I told, day before yesterday, beginning of the regulation methods, drop due to leakage reactance is EMF phenomenon, and drop due to armature reaction is MMF phenomenon. So leakage reactance can be represented with EMF phasor, armature reaction can be represented with MMF phasor or field current vector. They are correct. But earlier two methods, both are combinedly considered, either EMF vector or MMF vector. But in this method, what we are going to do, we will separate both. We will separate both drops. Drop due to leakage reactance is separated. Drop due to armature reaction, both are separately considered. And drop due to leakage reactance is represented with EMF phasor. Drop due to armature reaction can be represented with MMF phasor. And both can be separated by drawing the Portier triangle. Portier triangle. Mainly in this questions will be mainly based on the Portier triangle. How to draw the Portier triangle, that is important. We are going to see very, very clearly. Fine. So since we are correctly considering, this method gives the accurate results. This method gives the correct results. This method requires OCC and ZPFC. Let me write that. In earlier two methods, in earlier two methods, the synchronous impedance and MMF, two methods, the drop due to armature reaction and leakage reactance drop. Both are combinedly considered. Combinedly considered as either EMF vector, or MMF vectors. But in this method, both are separately considered. In this method, both are separately considered. And drop due to armature reaction, drop due to leakage reactance is considered with the EMF vector, and drop due to armature reaction. Is considered with the MMF vector, or field current vector, So they are correctly considered. That is, they are correctly considered. And these two are separated. These drops are separated. By drawing the Portier triangle. Okay. This is a separation of two drops. This method gives accurate results. Okay. And this method requires OCC and ZPFC. This method requires OCC and ZPFC, zero power factor characteristics. OCC and ZPFC, open circuit and zero power factor characteristics. Yeah. So let us draw the OCC and ZPFC. Taken now? Yes. Yeah. I hope you have taken. Fine. So Let us draw the OCC and ZPFC on the same graph. You know, OCC is E versus IF, ZPFC V versus IF, V versus IF. Draw the OCC and ZPFC. This is IF. Y-axis common E and V, E and V. Yeah. OCC and ZPFC. This is OCC, this is ZPFC, zero power factor characteristics. ZPFC. Fine? Yeah. OCC, ZPFC. On this, listen. I have given earlier E is equal to V plus IA ZS na IA XES RA neglected. E is equal to V plus IA XES. But for ZPF lagging, V0 plus IA at an angle minus 90 degrees, IA at an angle minus 90 degrees, E is equal to V0 ZPF lagging, IA at an angle minus 90 degrees and XS at an angle plus 90 degrees, That is equal to what? V plus IA into XES. E is equal to V plus IA into XES. Fine? Yes. And E minus V is equal to what? E minus V is equal to IA into XES. Just have idea about this. I will come back to this. Why I am explaining? ZPF lagging, zero power factor lagging load, current I have taken minus 90 degrees now. IA is equal to minus 90. XS always 90. Neglect RA. Neglect. Then E minus V is equal to, it is just arithmetic difference. I mean to say, here, the vertical distance, this is OCC say, and this is SCC, ZPFC. The distance between these two, the distance between these two, that is IA XES. That is equal to IA XES, dear student, because this is E and this is V. Vertical distance between practical OCC and ZPFC, that is equal to how much? IA XES. E minus V is equal to IA XES, na? Yes. For ZPF lagging only it is correct. Yeah. That's the main key point. Okay. Listen. Yeah. In this, first term, this is V say. I am taking this is V. For example, this is V. This is V phasor. For lagging power factor, this is IA, na? Yes. For lagging power factor, this is IA. Then this is IA. For lagging power factor, IA. Okay. Yes. IA. And this is main field MMF this side. This is a main field MMF. But you add IA, RA, IA XL. RA neglected. This is IA XL same. This is V phasor, V, and this is IAXL, say, IAXL drop. By adding IAXL drop, what is this? This is E. This is itself E. E is equal to V plus IAXL. You remember, E is equal to V plus IAXL. That is ER, not E, ER, air gap voltage. At the time of phasor diagram, I have drawn ER minus V is equal to IAXL. IAXL. Fine? Yeah. When this is ER means FR, the MMF, this is FR. What is FR? FR is MMF related to ER, 90 degrees. ER. And FA. FA will be to compensate armature IA this side. Na? If you want to take FA, right, on this side, FA to compensate armature reaction. Actually, armature reaction flux in this direction. If you take this side, that is armature MMF. But to compensate main field flux, how much FA will be taken in this direction? Dear students, FA you may be expecting to take on IA side. But strictly speaking, armature flux, I need to compensate armature flux means FA one direction, right? Armature flux one direction, main field flux. This FA I am taking main field flux. Then what is the total IFT? Total IFT. This is FT. See, this is FT. FT is equal to how much? FT is equal to FA plus FR. FT is equal to FR plus FA. FA. So what is FR? The MMF for air gap. MMF. FR is the MMF for air gap flux. FA is the field current to compensate armature reaction. FA or IFA. See, FR. FR is the EMF or the field MMF. Field MMF. MMF to generate air gap voltage. Air gap voltage. Air gap voltage means that is what? ER. ER is equal to V plus IAXL. V plus J into IAXL. RA neglected, say. V plus, strictly speaking, RA, you can neglect RA plus J into IAXL. J into IAXL. But this is very small, can be neglected. This can be neglected. Okay? Yes, IAXL. Then, if you have given IFR, FR or IFR, FRR, let me take IFR is the field current to generate air gap voltage, ER. Fine? Yes. The ER is equal to how much? Say ER is equal to nearly some 450 volts, say. 450 volts, say. That includes already you are generated the voltage. Generate the voltage and also you are compensating resistance drop and leakage reactance drop. Of course, resistance is negligible. But what is FA? FA will be FA. FA is MMF. FA or IFA, say. MMF to compensate. MMF to compensate the drop due to armature reaction. Drop due to armature reaction. Drop due to armature reaction. Leakage reactance already we have taken. That was added in FR. But here to compensate armature reaction FA. Now coming to our diagram. See. This is clear, na? FA and FR. FR is to generate the ER. Okay. Listen. If this is V, I am extending, dear students, see, important thing is, I am extending to here. What is this? This is V. This is the V. V rated. V is equal to V rated. That is V rated. Now, this is ER. If you take this is going to be ER. This is ER. This is ER, say. Now extend this point onto here. Extend this point onto OCC. Okay. Now, this is V, this is E. Can I say this is IAXL? Yes, this is nothing but IAXL. This is IAXL. Because this is V, IAXL. Yeah. And for that IAXL, I want to take ER a bit more. See. Yeah. Let me take, this is ER. Because on the diagram, then only you can identify. So that's the reason I am taking ER a bit. Yeah. Yes. See, this is IAXL. This is IAXL. Now, what is this? Can I say this is FR? Yes, this is FR. This is FR. FR. Now FT. If I want E is equal to what from this? E is equal to V plus all the drops. Here, E is equal to V plus IARA plus J into IAXL. E is equal to V plus IARA plus J into IAXL plus J into IAXA. So all this is nothing but ER, that is related to FR, but this is related to FA. So this is related to FT. This is related to FT, total field current. Total. So therefore, this I can say, this is nothing but total field current. Total field current, IFT. This is nothing but IFT or FT, say, total MMF, FT. This is FT, this is FR, means everything is arithmetic sum. So all they are in same phase, na? ZPF lagging, that is advantage. That is advantage. ZPF lagging, are you finding FA and FR both are adding? See, this is FR, this is FT. Can I say this is FA? Yes, this is FA. Dear student, that is FA. That is FA means this is nothing but FA. This is FA. This is height is IAXL. This is FA. So, this is called Portier triangle. Portier triangle. For example, if you take this is B, okay, this is D and this is H. The right angle triangle BHD is called Portier triangle. This triangle is called Portier triangle. Portier triangle. Portier triangle is a right angle triangle. Portier triangle is a right angle triangle. So base of the Portier triangle is represent MMF or IFA. It is MMF or IFA required to compensate armature reaction. But height of the Portier triangle, that is DH, is equal to IAXL. But even this point D is there, na? If you take here, the Portier triangle, this will be D dash, for example, D dash. This is B dash. H dash, it is same. Even if you take here also, this is same. The Portier triangle, D double dash, B double dash, and this is H double dash. These are same. The Portier triangle, you can right shift downwards, it will be same. Right? Yeah. The another point to note here is under short circuit condition, dear students, under short circuit condition, I have taken this. I am just projecting that the Portier triangle, you can project it like that. B dash and D dash will be, B dash is on the ZPFC, D dash will be on the OCC, because their magnitudes are same. Yeah. And also, see, under short circuit condition, while you are drawing ZPFC, what we have done, while you are drawing ZPFC, the first point on the ZPFC, is short circuit test. No? First point on the ZPFC is the short circuit test. In this, whatever the generated EMF is given, that is to drive the current. That is nothing but ISC. Na? At this point, first point on the ZPFC, short circuit test, ISC. Now for this, if you get the field current is given what for? We know E is equal to, simply it is IA into ZS. IA into ZS, that is equal to IS into XES. XESA nearly equal to. V is equal to 0. Since V is equal to 0, because it is short circuit test, 0. And then E is equal to IA into XES, that is equal to IA into XEL plus XEA. XL plus XEA. E is equal to IA into XES, that is IA into XL plus XEA. Therefore, first point on the short circuit test V0, can I say this is IFL plus IFA? IFL plus IFA, or it is FEL plus FA I can take. FEL plus FA. So, first point on the ZPFC, where here V is equal to 0, na? Here V is equal to 0. Short circuit test. So, first point on the ZPFC is the short circuit test. But what is the MMF required under that? The MMF required is FL plus FA. Field current to compensate leakage reactance drop plus armature reaction drop. Correct. IAXL is there, IAXA is there. Both are there. That is nothing but IAXL is there plus IAXA. IAXL plus IAXA. That E is equal to. Therefore, first point on the ZPFC, the field current is to compensate leakage reactance drop, compensate IAXL and IAXA. To compensate both the drops. So, you're getting this point. To compensate both the drops, that is measured from first point on the ZPFC. So, can I say this point as, dear students, here I can say this is FEL, the first point. This is total. This is nothing but FEL. FEL. This is FEL and this is FA. This is FA, correct? FEL and FA. Okay. Objective questions, these are only the thing. What is the base of the Portier triangle FA? Height of the Portier triangle. And this is nothing but FEL. So, if you extend the same point on this, the same diagram I am drawing here, how you can draw? Like this. It is parallel. These are same, na? Yes. These are like this. So we need to draw that from air gap line. It is parallel to air gap line. This line parallel to air gap line. So once this is FA means, important thing here to note is, important thing to note is this is IFL. This is FEL or IFL. FL or IFL. Okay, that point's enough. The procedure is there. Okay, procedure I can explain. Just to have idea about this. Portier triangle is there now. Height of the Portier triangle IAXL and base of the Portier triangle FA or IFA to compensate armature reaction. And this is FEL to compensate leakage reactance. Now coming to the steps. Don't worry much about this. These are the how it is coming. For example, if you ask a doubt, sir, how can you say this is FA, this is IAXL, FEL means compulsory, you need this much explanation. Right? Directly, if I give blindly, if you ask the doubts at the end, I cannot explain at all without all these things. So that's the reason I'm making very clear. But at the time of examination, forget about all these things. What is a Portier triangle? Already we have seen the reasons. Fine, reasons. Now coming to the methods, procedure, how to find the regulation, how to draw the Portier triangle, I have explained so far. Okay. Now I'm going to the method. Let us come to the method. Steps are like this. The steps. Draw the, once again I am drawing. Draw the OCC and ZPFC. We are going to complete quickly. It won't take much time later. Only that is mainly thing I wanted to explain. OCC. Okay. OCC, SC, ZPFC. I will write the steps also. OCC and ZPFC. Okay. Yeah. Draw the OCC. General statement I am going. Whatever I have explained so far only that is for zero power factor lagging, that is valid. Zero power factor lagging. But the Portier triangle is same for any load. And I am going to make the generalization to find the regulation for any given power factor. So this is the step. The steps I am going to write very clearly. See. Listen. Yeah. Draw the OCC, draw the ZPFC. You are also draw whatever I am drawing. I am going to write the steps. Draw OCC, draw ZPFC. And draw the air gap line. Draw the air gap line is which is tangent to the OCC. Draw the air gap line. Air gap line. This is air gap line. Air gap line. Next step is at V is equal to V rated. At V is equal to V rated. This is V is equal to V rated. At V is equal to V rated. Draw a horizontal line onto the ZPFC. Draw a horizontal line onto the ZPFC to meet at point B. To meet at point B. Okay, yes. To meet at point B. And I would like to take this is O and A point. O and A. O and A. That what is OA? Tell me. OA is equal to, just now I have given, OA is equal to FEL plus FEA. I have explained now short circuit test. First point on the ZPFC short circuit test, that is to compensate the drop, to compensate leakage reactance and armature reaction. So that much MMF is required. So this is field current or MMF. See, dear students, MMF, F, or you can take FL plus FA, FL plus FA. Okay. So first point is at V is equal to V rated, draw a horizontal line. At V is equal to V rated, draw a horizontal line onto the ZPFC to meet at point B. Next, draw BC. Draw BC is equal to OA. Draw BC is equal to OA. BC how much? This OA. BC is equal to OA. Then draw CD parallel to air gap line. CD parallel to air gap line. Parallel to air gap line. These two are parallel, this and this, parallel to air gap line. Then join BD. Join BD. Join BD. And draw DH perpendicular to BC. Draw DH perpendicular to BC. Now, this right angle triangle BHD is called Portier triangle. Right angle triangle BHD is called Portier triangle. This is what I have explained earlier. So much time I have took. Now I am coming direct statements. This right angle triangle is called Portier triangle. BHD is called Portier triangle. And the base of the Portier triangle, is equal to FA, MMF to compensate armature reaction, or you can take IFA also, IFA, FA, MMF. And height of the Portier triangle is equal to IAXL. Height of the Portier triangle is equal to IAXL. Is a drop due to leakage reactance. Drop due to leakage reactance. Then what is CH? CH is equal to FEL. Is the MMF to compensate the leakage reactance drop. FEL is to compensate leakage reactance drop. Right? Yeah. So these are the steps for Portier triangle. Once again, let me repeat within a minute whatever I have explained. Listen, the steps are draw the OCC, draw the ZPFC, and draw air gap line. First step, draw air gap line. Next step, at V is equal to V rated. For example, 400 volts say. At V is equal to V rated, draw a horizontal line onto the ZPFC to meet at point B. Next, draw BC is equal to OA. So OA 4 centimeters, BC also equal to 4 centimeters. Draw BC is equal to OA. Then draw CD parallel to air gap line. Then join BD. Then draw DH perpendicular to BC. DH is perpendicular to BC. This is a perpendicular to BC. Now, this right angle triangle BHD is called Portier triangle. Then the base of the Portier triangle BH is equal to what? FA or IFA, field current or MMF to compensate armature reaction drop. Now, height of the Portier triangle DH, that is IAXL, is a drop due to leakage reactance. And CH is the MMF or field current to compensate the leakage reactance drop. Okay? The DH, some 20 volts DH drop due to leakage reactance say. How can you compensate? Extra field current to be given. How much extra field current? CH. The CH is related to IAXL. IAXL 20 volts drop say this much extra field current has to be given. Right? Yes. But we will take IAXL, EMF phasor, drop due to leakage reactance is taken EMF, and armature MMF. So let me write the steps for construction of the Portier triangle. Okay. First one, draw OCC steps. Draw OCC and ZPFC. Draw OCC and ZPFC and air gap line. Draw OCC, ZPFC and air gap line. Air gap line is tangent to that. Next step is at V is equal to V rated. V is equal to V rated. Draw a horizontal line. Draw a horizontal line. Horizontal line to meet at point B. To meet at point B. To meet at point B. To meet at point B on ZPFC. To meet at point B on ZPFC. Draw a horizontal line onto the ZPFC. Onto the ZPFC to meet at point. To meet at point B. To meet at point B. Okay. Next step is, next step. Draw BC is equal to OA. BC is equal to OA. BC is equal to OA. Next, draw CD parallel to air gap line. Draw CD parallel to air gap line. Draw CD parallel to air gap line. Next, join BD. Join BD. Next, draw DH. Draw DH perpendicular to BC. Draw DH perpendicular to BC. Then the right angle triangle. The right angle triangle BHD is called Portier triangle. Is called, questions is asking mainly on the Portier triangle. Base to height to is called Portier triangle. Portier triangle. The height of the Portier triangle, the base of the Portier triangle, the base of the Portier triangle, the base of the Portier triangle BH is equal to FEA or IFA. IFA. MMF to compensate, MMF or field current to compensate armature reaction. To compensate armature reaction. And height of the Portier triangle. Height of the Portier triangle DH is equal to what? IAXL is a drop due to leakage reactance. Drop due to leakage reactance. Drop due to leakage reactance. Fine? Yeah. Next up, CH is equal to IFL. CH is equal, you have taken up to here now? Yes. CH is equal to IFL. Yeah. CH is equal to IFL. CH is equal to FEL or that is IFL. Field MMF. Field MMF or current. To compensate the drop due to leakage reactance. to compensate the drop due to leakage reactance. Leakage reactance. Okay. Yeah. Leakage reactance. 5. Now, the next step is what to do. This is the procedure to construct the Portier triangle. Directly I am giving final steps how to draw. Simple way. Simple way. And we have seen everything reasoning. Why it is FA, everything I have shown. Okay. Now, after measuring XL, after measuring IA-XL from the Portier triangle, then calculate ER. Calculate ER. For general power factor, we are finding whatever I have shown on the diagram, very beginning diagram, it is for ZPF lagging only. But I want to find 0.8 lagging means ER is different. ER is different. For that we are finding. But Portier triangle height IA-XL FA, that is fixed. So next step is after measuring IA-XL from Portier triangle. From Portier triangle, after measuring IA-XL, then calculate ER. Calculate ER. That is ER is equal to what? ER is equal to V plus IARA plus J into IA-XL. That is equal to square root of V cos phi plus IARA whole square. V cos phi plus IARA whole square. V sin phi plus or minus IA-XL whole square. XLA, I am not taking XA. IA-XL adding means ER you will get. ER you will get. Right? But in this diagram, if you use ZPF lagging, you will get the same whatever I have explained from the first diagram. ZPF lagging, whatever I have explained, V and ER both are in same phase. Both are in same phase. ZPF lagging. But other power factor, there's some phase difference will come. V and ER is not in same phase. Their phase difference will come. Only ZPF lagging, both are in same phase. V and IA. But we are taking general power factor. Yeah. V cos phi plus IRA whole square. Next step. Measure IFR. Measure the field current. Field current or MMF. Field current or MMF. Or MMF. MMF FR. FR. From OCC corresponding to ER from OCC. ER from OCC. Measure the field current or MMF. Field current or MMF. Or MMF corresponding to ER from OCC. ER from OCC. Field current or MMF from OCC. That I will go for graph, no? See, the meaning is, listen. We know that ER we are calculated, na? ER we are calculated. ER. See, this is ER we are calculated. For that ER, this is ER, say for example, ER. We have got ER here. From this, voltage, and then simply I can extend on to this. This is your IFR. This is your FR. FR. Dear students, FR. Or IFR, field current. FR. I know voltage. I am coming like this. I know voltage. And we are coming to here. And finally coming back to here. That is FR. FR. Actually, this method in your BTech, they can ask for full question, 16 marks question. Gate examination. See how simple questions they are going to ask. What is the possibilities that we will see. But this is useful for those who are doing the BTech also. FR. ER, you know, for that ER, we are getting FR. Okay, yes. Now, the FR includes what? FR includes, if you are generating this much voltage ER, say, FR is given, it is generating, ER means V plus IA RA drop, IA XL drop is taken care. FR I have measured. See, concentrate here. If I am generating ER, say, ER I am generating, so that you are taking care about V. V is maintaining, resistance drop also compensated, leakage reactance drop also compensated. Leakage reactance drop also compensated. V, you are maintaining 400 volts, resistance drop, leakage reactance. You are generating ER. For that, FR is required, MMF. For field current IFR is given, you are maintaining all these things. Now, which drop to be considered? Now, which drop is not yet considered? Armature reaction not is considered. Armature reaction drop is not yet considered. We are only at ER. Now, if you add armature reaction drop, then you will get E, full total generated voltage. Therefore, next step what to do? Add both. Add FA to FR. FA to FR vectorially. We need to add FA to FR vectorially. That is like this. FR, we know, FR. FR. And then FEA, for lagging power factor, FEA you have to take. FA. Now this is FT. Total MMF, FT. Okay. For FT, again measure E0. E0. Next step is measure E0 corresponding to FT from OCC. E0 corresponding to OCC. Okay, FT. You calculate FT na? For any general power factor I am taking, dear student, general power factor. Whatever we have explained, it is only for ZPF lagging, first very beginning. But we are making general power factor. Yeah. FT. Now go back to this diagram. If this is FT, say, yeah, this is FT. This is total FT. For this FT, is the last step. FT. Measure E0. Measure E0. Measure E0. Is E0. Then regulation is equal to E0 minus V by V into 100. E0 is the total generated EMF. FT is there now for total MMF. Total MMF is total generated EMF E0. So then the regulation is, lastly, regulation is equal to E0 minus V by V into 100. Over. This method is over. Okay. The procedure. Fine. Okay. Now you may question, sir, you have explained 1 hour this method. What is the type of questions you can expect? The questions will be based on the mainly Portier triangle. Let me give some examinations. The questions are like this. Over na? Yeah. The questions are, he has given Portier triangle is given directly. Portier triangle is given. On the Portier triangle, this is B, okay, C, D, H, right? The segment BH, refers to A bit, IA, B bit, IA, XCL, C bit, IA, XCA, D bit, IA, XCS. Tell me what is the answer for this? The segment B, indirect questions. The segment BH refers to what? BH refers to what? IA, XCL, IA, XCA. What is your answer? Tell me. Dear students, what is your answer? Hello? Yeah. Exactly. BH, yeah, losses correct. Whatever you say, losses, but what is the drop? Not losses. Armature reaction does not cause this. What is your answer? BH is equal to IFA or FA directly. MMF, IFA or FA. BH is equal to, we know that BH is equal to FA or that is or IFA. What? Field current to compensate armature reaction. But that options are not given. Na? It is nothing but compensate for drop. That is to compensate armature reaction drop. IAXA. So therefore, your answer would be this one. C. Fine. In the same question, I may ask in the same question, DH refers to what? Tell me. DH refers to another question. DH refers to same option. DH refers to dash. What is your answer? Options are same. IA, RA, IA, XL, IA, XA. What is your answer? Options are same. What is your answer? What is your answer? Answer is? Yes, exactly. IAXL refers to IA. Very good. IAXL. Because DH is refers to what? IAXL. IAXL drop. And what is CH refers to? Or strictly speaking, this is DH is equal to. No. DH is equal to. That is IAXL. If I ask, CH refers to what? CH refers to dash. CH refers to P. Answer B. IAXL. That is IAXL. Okay. These are some kind of indirect questions. Another question. The question is like this. DH is equal to 100 volts. DH is equal to 100 volts. IA is equal to 20 amperes. Then XL is equal to how much? XL is dash. How much XL? DH 100. IA 20. IA XL is equal to how much? See. DH is equal to IA XL, no? Yes. Then XL is equal to what? DH by IA. DH is 100 volts, IA 20, that is equal to 5 ohms. XL is equal to 5 ohms. 5 ohms. XL is 5 ohms. Yeah. Okay. And GATE question, let me give. GATE 2003 examination, he has given one question. Question is like this. Is given OCC and SCC. This is OCC, ZPFC. OCC and ZPFC. ZPFC, this is E versus V. This is the line segment is given. V is equal to 1 per unit is given. This is V is equal to 1 per unit is given. P and Q. Okay, the segment PQ represent. The PQ represent drop due to A bit. Drop due to leakage reactance. Drop due to leakage reactance B bit. 4-tier reactance C bit. 4-tier leakage both are same. Synchronous reactance and magnetizing reactance. B bit is magnetizing reactance. Now, what's your answer? Tell me. Answer. Yeah. Answer is synchronous reactance. This we have seen a V is equal to V rated. The vertical height between both. OCC and ZPFC. That is nothing but what? IAXES. Right? Why? Because I have shown E is equal to V plus IA into XES. This is ZPFC, zero power factor characteristics. V0 plus IA at an angle minus 90 degrees. XS at an angle plus 90. So therefore V plus IA into XES, E is equal to, or E minus V is equal to IA into XES. So therefore the vertical height between OCC and ZPFC is the drop due to synchronous reactance. This already I was explained. Okay, remember these things. Fine. Yeah. So I have given full information for you. Nothing is there. Each and every point have been explained, right? Just see once again. That will be enough. Reasons already now. Quadratic triangle, how it is coming, I have explained. Then don't see why how it is coming again every time. You know, BH is equal to what? CH is equal to what again? That is enough. Okay, and vertical height between. Yeah. Yeah, now it is better to take break for some time, right? And then after that, ASA method, I am not going to explain totally. For ESC students, I will explain at the time of prelims examination. After prelims examination, I will draw the ASA method also fully. Okay. And ASA method, nothing is there. Only saturation will be taken. Only drop due to saturation is taken. That is extra. Drop due to saturation. Fine? Yeah. Or else let me complete that also. It's a matter of 5 minutes I will close. 5 minutes we will go for break. Dear students, 5 minutes we will close. Stay for some time. ASA method. So that after the break, we are going to start interested topic, short circuit ratio. Short circuit ratio is very interested. And yeah, now let me complete this ASA method. See, ASA method. ASA method. In ASA method, in this method, drop due to saturation is also considered. Drop due to saturation is also considered. Other methods not considered. This is only the point you can remember. Drop due to, in this method, It is similar to ZPF only. ZPF only, zero power factor. In this method, the drop due to saturation is also considered. Drop due to saturation is also considered. Is also considered. This is the most accurate method. This is most accurate method. Fine? Yeah. Drop due to saturation is also considered. Where is the drop due to saturation? If you take OCC, draw the air gap line. If you draw the horizontal distance between this and this, if have given this much of field current, say, if there is no saturation, we can expect this much voltage. This much voltage. But due to saturation, I am getting only this much voltage. Right? For the same field current. This is the drop due to saturation. Drop due to saturation. Drop due to saturation. The vertical height between ideal OCC, air gap line, and practical OCC. That is nothing but drop due to saturation. This is OCC. This is air gap line. Air gap line. The vertical height between, the vertical distance between ideal OCC and practical OCC. OCC is the drop due to saturation. Drop due to saturation. Okay, drop due to saturation. To compensate saturation, also extra field current is required. Some extra field current is required to compensate saturation. That again can be measured from the ZPFC characteristic. Leave it. Procedure not required. Again, it will take 1 more hour. Why unnecessary waste of time? No need of it. It is also, again, you have to draw the ZPFC zero power factor and the Portier triangle you need to write. You need to draw. Nothing extra will come. Nothing extra point will come. And finally, we are going to see that saturation. That's enough. That's enough. Important thing is regulation by this method. Tell me, regulation by ASA method will be little greater compared with regulation by ZPF. Both are accurate only, but when comparatively, which method will give the little more regulation? ASA. ASA will give the little regulation because regulation is more, since drop due to saturation is extra. Drop due to saturation is extra in ASA. Extra in ASA. Okay, drop due to saturation is extra in ASA. Saturation drop is extra, regulation is little more. Fine? Yeah. So we are completed all 4 methods, 4 plus 1, 5, because synchronous impedance saturated and also unsaturated. Saturated, unsaturated. Yeah. Now, the examinations question will be comparative all methods, comparatively all methods. He will give this regulation method and this side percentage regulation. Match the following. Match the following. Such type of questions can be answered like this. This is the regulation in various methods. The regulation in various methods in descending order. In descending order. Descending order. Which method will give more regulation? Which method will give more regulation among all methods? EMF. EMF method is more. First method, pessimistic method, na? EMF అంటే unsaturated. After that, saturated synchronous reactance method. Saturated synchronous impedance method. First one is unsaturated. EMF అంటే unsaturated, saturated synchronous impedance. After that, ASA method. Next, ZPF. Which is the least? MMF method. Have idea about these things. Okay, yes. These are the voltage regulation, descending order. Right? Now I will use one question and then we'll go for a break. Question is, match the following. Match the following. This is regulation method. It's a method and percentage regulation. This is the method. Percentage regulation. See, P, Q, R, S. 1, 2, 3, 4. This is EMF method and this is MMF method, ZPF method, saturated synchronous impedance method. Say saturated synchronous impedance or reactance. Saturated impedance or reactance method. This side 20% and this is 30% and this is 15%. Say this is 25%. Now A bit P1, Q2, R3, S4, like B, C and D. Tell me the answer. I'm not writing all the options, but you tell me the answer, then we will go for break. Already we are late. But this regulation method, time consuming. Anyhow, we are completed. And after the break, we are going to see very interested topic. Total objective oriented topic in all competitive examinations. Short circuit ratio. We are going to see after the break short circuit ratio. Okay. Yeah. What is your option? EMF method is maximum na 30%. Okay. MMF is minimum. It is 3. And among ZPF and this will be the ZPF and this is this. So therefore your answer will be P2, Q3, R1, S will be 4. Okay, this is the correct option. Right? Yeah. Now let us take break for 15 minutes. Roughly 15 or 20 minutes. Let us take break 20 minutes. Break for 20 minutes. Class will start at 7:47. 8:05. Okay, take the break and then come back.
Hello.
Yeah. Welcome back. Yeah, are you there? Yeah. Right. Yeah, yeah. The class will be till 9. I will try to close. Okay, don't worry. I will try to close at 9. Right. Okay. Now let us start the next method. Next method is short circuit ratio. The another important discussion is short circuit ratio. Short circuit ratio, SCR. SCR. The short circuit ratio is one of the important specification of a synchronous machine. It is also one of the important specification. For example, if you want to find a synchronous machine, say if you want to purchase an alternator. So how to purchase an alternator? You have to give all the quotation to be given. Quotation means, so what is the rating of alternator you want? What is the voltage rating, current rating, power factor? Is it lagging or leading? And what is its frequency? Everything you need to mention. You have to mention. Along with that, you need to mention the short circuit ratio also. You have to mention short circuit ratio. So SCR is equal to, I want SCR is equal to 1 or 1.5, 0.9. Based on the short circuit ratio also, the performance of the machine depends. Performance of the machine. Performance means that is how the size of the machine, cost of the machine, stability of the machine, voltage regulation, all that also depends on the short circuit ratio. So this is one of the important specification of the synchronous machine. Okay, yeah. So SCR is one of the important specification of a synchronous machine. Specification of synchronous machine. Based on SCR, the performance depends on performance of the machine is also depends on SCR. It also depends on SCR. Let us see first what is this SCR? Definition of SCR. Listen. Short circuit ratio. It is the ratios of the field current. Ratios of the field current. IFM by IFA or FM by FA. It is the ratios of the field current. The field current required to generate rated voltage under short circuit condition by the field current required to produce rated armature current under short circuit condition. Short circuit condition. The SCR definition is short circuit ratio. It is the main field current required. The main field current required to generate rated voltage. To generate rated voltage under open circuit condition. Open circuit condition by the main field current required. The main field current required to produce rated armature current under short circuit condition. Under short circuit condition. Short circuit condition. The field current required to generate rated voltage under open circuit condition and field current required to produce rated armature current under short circuit condition. That is equal to SCR. So SCR is equal to IFA, IFM by IFA, IFM by IFA, or FM by FA. Okay. Yeah. So I think you remember that. What is that? The OCC, open circuit condition. You want rated voltage, na? Rated voltage. EOC is equal to V rated. Say for example 400 volts. What is the field current required? This is called IFM. Similarly, under short circuit condition, the field current required, that will be the IFA. IFA, ISC is equal to IA rated. Say that is some 20 amperes, say 20 amperes. Say. So this IFM by IFA, that is said to be SCR. IFM by IFA, that is SCR. So main field current required to generate rated voltage under open circuit condition divided by the main field current required to produce rated armature current under short circuit condition. IFM by IFA, clear? Yes. That is equal to 1 by ZS saturated per unit. 1 by ZS saturated or adjusted. It is also called adjusted. 1 by ZS saturated or adjusted per unit. That is also nearly equal to 1 by XES saturated or adjusted per unit value, per unit. This is a derivation. I will derive at the end. First, take down this relation. SCR is equal to 1 by ZS saturated per unit, not unsaturated, saturated per unit, or nearly equal to 1 by XS saturated adjusted per unit. How this is coming, I will derive at the end after seeing all the conclusions. And SCR for various machine, SCR for value 0.6 to 0.9 for cylindrical rotor synchronous machine. For cylindrical rotor synchronous machine, 0.6 to 0.9 and 0.9 to 1.5 for salient pole synchronous machine. For salient pole synchronous machine, and 0.4 for synchronous condenser. 0.4 for synchronous condenser. You know what is synchronous condenser? Overexcited synchronous motor under no load condition. Overexcited synchronous motor under no load condition is called synchronous condenser. Okay. So these are the values. SCR is equal to 0.6 to 0.9 for cylindrical rotor machine. 0.9 to 1.5 for salient pole synchronous machine. And 0.4 for synchronous condenser. Okay. These are the optimum values. In this, each and every step is one objective questions. Dear student, each and every one is objective question. Like first one, definition is itself objective question. In your previous examination, you can find the question like this. Definition, based on the definition of the short circuit ratio, question is given, choose the wrong options. Generally, it will be given right options. No, you need to choose right options. But sometimes, so old GATE examinations, there is also type of questions, choose the wrong options. 4 options are being given, right? Among that, you have to choose wrong option. It is given like this. The options are given: armature reaction for lagging power factor, 0.8 lagging power factor, demagnetization, cross magnetization, and XD greater than XQ. Like different options. One option also it is given based on the SCR. One option is given. I will read out that option. Tell me whether it is right or wrong. It is given like this. Short circuit ratio is the ratio of main field current required to generate rated voltage under open circuit condition to the main field current required to produce rated armature current. Rated armature current. Tell me, is it right or wrong? Is it right or wrong? Okay. Are you getting? Let me read out this statement again. SCR is a ratio of main field current required to produce rated voltage under open circuit condition to the field current required to produce rated armature current. Right or wrong? Very good. It is wrong. Why wrong? Tell me. Why wrong? Because under short circuit condition is missing. Short circuit condition is missing. Because short circuit condition field current is different. Load condition field current is different. So that must be OC condition divided by denominator must be SC condition. Both are the field currents. Okay. Yeah. And also another examination, the SCR. SCR is there in IFM by IFA. He has given SCR. SCR is options are. SCR is A bit. Options are 1 by ZS saturated, 1 by ZS unsaturated, 1 by ZS saturated per unit, 1 by ZS unsaturated per unit. It must be 1 by ZS saturated per unit compulsory. I will derive that. 1 by ZS saturated per unit. If per unit is missing, say, per unit is missing. First of all, what is the units for SCR? Tell me, what is the units for SCR? No units. Why? Because they are simply ratios of the currents, ratios of the field current, IFM by IFA, ratios of the field current. Okay, no units. That's the reason 1 by Z is saturated per unit, no units. If it is per unit is missing, 1 by Z. 1 by Z is nothing but 1 by ohms. Mhos. SCR becomes mhos. No, which is wrong. Per unit compulsory. And that to be saturated per unit, not unsaturated, saturated. Similarly, these options are there now. SCR is 0.6 to 0.9, 0.9 to 1.5, 0.4. These are itself objective questions. I will ask one question for you. Tell me the answer for this. The question is like this. The question may be, see, the question is, SCR, the excess per unit for synchronous condenser. For synchronous condenser is A bit 0.4, B bit 1.5, C bit 2.5, D bit. D bit 1. What is your answer? Tell me. Excess per unit for synchronous condenser is. What is the answer? Okay. Answer is 2.5. Correct? It will be 2.5. Why 2.5? We know SCR is 0.4. SCR 0.4. Excess per unit is equal to 1 by SCR. 1 by SCR. Okay. That will be 2.5. Simple questions. Yeah. Now, then let us see the important significance of SCR. As I told, this is one of the important specification of a synchronous machine. What is the importance of it? What is the significance of it? Let us see. Significance of SCR. Significance of SCR. Significance of SCR. SCR is equal to 1 by XS saturated per unit. Correct? Saturated per unit. It means SCR is inversely proportional to XS, inversely proportional to XS, but that is inversely proportional to XA. Inversely proportional to XA. And that is inversely proportional to armature reaction. Inversely proportional to armature reaction. Why? Because XA is proportional to armature reaction. XA is proportional to armature reaction. So from this, what we can understand from this relation, tell me, from this relation, SCR is inversely proportional to armature reaction. SCR is inversely proportional to armature reaction. Or armature reaction is inversely proportional to armature reaction is inversely proportional to SCR. Armature reaction is inversely proportional to SCR. Therefore, if SCR is small, say, Small value of SCR indicates what? Large effect of armature reaction. Large effect of armature reaction. Therefore, there is a large variation of terminal voltage. The machine is more sensitive with respect to terminal voltage for load variation. When load is increases or decreases, say, voltage also increases or decreases. Voltage variations are more. Voltage variations are more. Machine is more sensitive with respect to terminal voltage. That is, small value of SCR indicates. Small value of SCR indicates the large effect of armature reaction. Large effect of armature reaction. Armature reaction. Therefore, the machine is more sensitive. Machine is more sensitive with respect to terminal voltage. With respect to terminal voltage for load variations. For load variations. That means voltage variations are more voltage variations. More voltage variations. More voltage variations. The drop, when load decreases, voltage increases. When load increases, voltage decreases. Load variations are more. In other words, drop is more or rise is more when load changes. That is one. Next statement. See, we know voltage regulation is proportional to armature reaction. This already we have seen at the time of regulation. Voltage regulation is proportional to armature reaction, but armature reaction is inversely proportional to SCR. Correct? Yes, SCR. Voltage regulation is proportional to armature reaction, that is inversely proportional to SCR. Therefore, small value of SCR indicates. Small value of SCR indicates the large effect of armature reaction. The large effect of armature reaction. Large effect of armature reaction and more. Regulation is more or poor or bad voltage regulation. Regulation is more means poor or bad. More or poor or bad voltage regulation. Voltage regulation. Okay. Regulation is poor. On this, one of the question in PG set 2017, he has asked the question. Small value of SCR indicates A bit. Good regulation, B bit. More regulation, poor regulation, good regulation, poor regulation. No significance on the regulation. SCR is small means poor regulation. Regulation is more means poor, bad regulation. Okay. Yeah. Now, then let us relate with the air gap length, size of the machine. Yeah. Okay. Taken this now? Yes. Yes. See? SCR, air gap length, armature reaction inversely proportional to air gap length. Armature reaction inversely proportional to air gap length. Why? Because See, this is the stator. This is a stator and this is a rotor. Rotor. Okay. And armature poles are formed. See, this is armature poles, north pole and south pole are formed. This is a rotor. This entire thing is rotor. This is a rotor. Rotor. But armature flux, path for the armature flux is how armature flux will take place from north pole to south pole. This is armature flux. Armature flux take place north pole to south pole. Right? Yeah. This is the phi A, armature flux. This is rotor. What is this? This is rotor. And the armature flux, magnitude of armature flux is depends upon what? Air gap. So the armature flux is offering reluctance only here, here and here. Armature flux, it is offering reluctance here and here. Correct? Yes. Only these 2 points. Air gap, in other words, air gap. So flux is equal to, flux is equal to what? Armature flux. Armature flux is equal to phi A. Armature flux. Phi A is equal to MMF by reluctance. Armature MMF by reluctance. But reluctance is proportional to air gap length. Reluctance is proportional to air gap length. And we know armature reaction is proportional to armature flux, but armature flux is inversely proportional to air gap length. Therefore, armature reaction is inversely proportional to air gap length. Correct? Yes, armature reaction is inversely proportional to air gap length. So, if you relate these things, armature reaction inversely proportional to air gap length. Armature reaction is inversely proportional to air gap length. And that is also inversely proportional to SCR. You have seen already, armature reaction is inversely proportional to SCR, correct? Yes. We have got already conclusion. Now, how air gap length and SCR relates both? SCR and air gap length, both are proportional. From this, air gap length is proportional to SCR. Air gap length is proportional to SCR. And when air gap length is larger, size of the machine also large, na? Air gap length is large means size of the machine also proportional to SCR. Size also proportional. And cost also proportional to SCR. Cost of the machine also proportional to SCR. Cost also machine is proportional to SCR. Therefore, if your machine is having, therefore, large value of SCR indicates, if SCR is large value of SCR indicates large air gap length, large size, and more cost. Machine is costly. The machine will be costly. Large value of SCR indicates large air gap length, large size, and machine is costly. More cost. Okay? Yes. Similarly, let us relate with other things, with power also. Let us relate with power also. Yeah. Taken, yeah. Power. The power output is equal to power P. P is equal to EV by XS sine delta. Of course, you are going to get this relation. Power is equal to EV by XS sine delta. The power is inversely proportional to XES. Power is inversely proportional to XES, but that is proportional to SCR. SCR is inversely proportional to XES. SCR is equal to 1 by XS saturated per unit. Therefore, power is also proportional to SCR. Power also proportional to SCR. SCR is large means power output is more. Machine power output also more. Similarly, next point with respect to synchronizing power coefficient. Synchronizing power coefficient. Synchronizing power coefficient, or it is also called stability factor. Stability factor, PSY. PSY. Stability factor, PSY. And that PSY is also one of the specification of synchronous machine that measures the stability. And also PSY is equal to what? PSY is equal to dP by d delta, derivative of the power. Derivative of power. That is d by d delta. Power is what? EV by XS sine delta. EV by XS sine delta. That is equal to EV by XS cos delta. Cos delta. Okay. EV by XS cos delta. Synchronizing power coefficient or stability factor, PSY. And this PSY measures degree of stability. What PSY indicates? It measures degree of stability. And we are going to see this separate topic. We are going to derive power equation and synchronizing power dP by d delta. Elaborate discussion, separate topics there. But here I wanted to give all the points related to SCR in the same page. Let us have all conclusions simultaneously here. Elaborate discussion of this synchronizing power coefficient we are going to see later. But how much it is required for this SCR topic I am discussing. Okay. But PSY measures the degree of stability. That's the reason it is stability factor. PSY measures the degree of stability. Degree of stability. Degree of stability. Therefore, stability is proportional to PSY. But PSY is inversely proportional to XES. That is proportional to SCR. That is proportional to SCR. Therefore, from this, stability also proportional to what? Stability is also proportional to SCR. Stability is also proportional to SCR. So large value of SCR indicates machine is more stable. Large value of SCR indicates. Large value of SCR indicates the machine is more stable. The machine is more stable. Machine is more stable. Fine? Yes. And another point of view, synchronizing power. Synchronizing power. Synchronizing power, PS. It's said to be PS. Synchronizing power, PS is equal to PSY into del delta, where del delta is the change in load angle. PSY is the synchronizing power coefficient, that is equal to EV by XCS cos delta into del delta. Okay, del delta is change in load angle. Due to disturbance. This again we are going to see, don't worry now. Because if I discuss this in detail, our SCR will go a side topic. It will be sided. The main topic is SCR. Fine. Just accept it. We will see again. So therefore, what you are observing, PSY is inversely proportional to XCS synchronizing power, that is proportional to SCR. Therefore, PS also proportional to SCR. Synchronizing torque is also synchronizing power, also proportional to SCR. Similarly, even synchronizing torque also proportional to SCR. Synchronizing torque also going to be proportional to SCR because power, they are proportional to SCR. Yeah. From all our discussion, okay, from here onwards, if you see, from here onwards, we can find all they will be proportional only, na? All they are proportional to each other. Except armature reaction, voltage regulation, all remaining things are proportional. So therefore, let me make your job easy. Then instead of seeing all the things, let me write all conclusions at a place so that you can easily remember. That is, conclusions are armature reaction. Armature reaction is inversely proportional to SCR, and voltage regulation also inversely proportional to SCR. Okay, yes. And air gap length is proportional to SCR. Size of the machine also proportional to SCR. Cost also proportional to SCR. And power output also proportional to SCR. Synchronizing power coefficient also proportional to SCR. And stability also proportional to SCR. Synchronizing power PS also proportional to SCR. Synchronizing torque. This is synchronizing power. That is synchronizing power coefficient, and this is synchronizing power. And this is synchronizing torque. All they are proportional to SCR. All these are proportional to SCR. Okay? Yes. Fine. Remember this table. Except first two, all they are proportional, na? Yes. All these are proportional. Right? Yes. And when all these are proportional, the directions are questions are direct. But indirect questions, how it will be? See, the air gap length is proportional to SCR. Stability also proportional to SCR. Just to compare these two statements, I mean to say, air gap length is proportional to SCR, and stability also proportional to SCR. Now from this, can I say stability is proportional to air gap length? Yes. From these two, stability is proportional to SCR. Stability is proportional to air gap length. Stability is proportional to air gap length. Correct. From these two, this if you take and this if you take, both are proportional, means stability is proportional to air gap length. Not only that, stability is proportional to PSY. All this left side also proportional. Left side, right side proportional to each other means all left side also proportional to each other. Stability proportional to air gap length, stability proportional to PSY, stability proportional to synchronizing power. All these will be, all they are proportional to each other. Correct? Yes, all are proportional. Only I want to highlight this stability proportional to air gap length. Generally, in synchronous machine, they are designed with large air gap length. Synchronous machines are designed with large air gap length to improve the stability. Mainly voltage stability. Because when air gap length is more, less effect of armature reaction, dear students. When air gap length is more, less effect of armature reaction is less. When armature reaction is less means less voltage drop. Voltage fluctuations are less. Voltage is nearly constant. Machine is more stable. Voltage stability is good. That's the reason synchronous machines are designed with large air gap length to improve the stability. Whereas induction machines are designed with small air gap length. To operate at better power factor. You may be knowing already. I am going to give all the points. Listen first. Induction motors are designed with small air gap length to operate at better power factor. Because when air gap length is more, induction motor will draw large magnetizing current, reactive current, I sin phi component, large magnetizing current. I think you may be knowing. If you see transformer and induction motor, you compare transformer and induction motor. Magnetizing current in transformer, it is only 4%, 5%. Magnetizing current, very less in transformer. Why? Because there is no air gap, closed path in transformer. But in induction motor, the flux will crosses the air gap. So magnetizing current is 30 to 40%. In transformer, it is 3%, 4%, say. But whereas in induction motor, 30 to 40%. Why? Because of air gap length. If air gap length is still more, when air gap length is more, then it will draw large magnetizing current. That is reactive current. I mu means I sin phi. It will draw large reactive current. Machine operated at poor power factor. That's the reason the machines are designed with small air gap length induction motors to operate at better power factor. But whereas induction motor, synchronous machines, they are designed with large air gap length to improve the stability. Power factor is not a problem. In synchronous machine, power factor can be controlled with field excitation. It can be operated at any desired power factor. You can operate your synchronous machine at lagging power factor, leading power factor. If you want unity power factor also, you can operate. Power factor control is in our hand. Synchronous machine, power factor control is in our hand. So no problem with the synchronous power factor. Only problem is stability. So therefore, to maintain the stability, they are designed with large air gap lengths. Okay. So let me write this statement. Generally, synchronous machines are designed. Generally, synchronous machines are designed with large air gap length. Large air gap length to improve the stability. To improve the stability. But induction machines, induction motors or designed with small air gap length. Designed with small air gap length. Small air gap length to operate at better power factor. To operate at better power factor. Better power factor. Whereas in synchronous machine, the power factor can be controlled. Power factor can be controlled. It can be operated. Can be operated at any desired power factor. At any desired power factor. Okay, desired power factor. Irrespective of air gap length, it can be operated at any power factor. Stability is the important criteria. Stability is the important criteria. Stability is the important criteria. Okay. That's the reason air gap length of synchronous machine is 3 to 4 times that of induction motor. Air gap length is 3 to 4 times when compared with synchronous machine. Air gap length of synchronous machine is equal to 3 to 4 times air gap length of induction machine, induction motor, induction machine. 3 to 4 times. Okay. So largest air gap length in synchronous machine. In all rotating machine, large air gap length in synchronous machine. There was also one question, right? Choose the correct options regarding the air gap length. I will give the conclusion straightforward. What is that conclusions? Air gap length of synchronous machine. Air gap length of synchronous machine is more compared with air gap length of synchronous machine is more compared with air gap length of DC machine compared with air gap length of induction machine. So the air gap length of induction machine is minimum. Synchronous machine is maximum air gap length. Air gap. Okay. So these are the conclusions regarding the SCR, short circuit ratio. Okay. In this, each and every statement is objective question. I have given this table now. All answers are there in the table. Now all these are in your fingertips. Armature reaction, voltage regulation, except that remaining things are proportional. Okay. In numerical problems, I will give one question in your previous GATE examination question. The GATE 2007, he has given 2 marks. Question is like this. The question is EOC is equal to V rated at IF is equal to 15 amperes, and ISC is equal to IA rated. IS is equal to IA rated at IF is equal to 10 amperes. Okay, yeah. Then the ZS excess saturated per unit. Excess saturated per unit is A bit. A bit is 1.5, A bit is 0.5, B bit 1.5, C bit is 0.67, D bit is 0.67, 1.732. What is the answer? EOC is equal to V rated, IF 15 amperes. what is the excess saturated per unit? See that excess saturated per unit is ISC is equal to IA rated. Now first let me find SCR. SCR is equal to IFM by IFA. IFM by IFA. What is IFM? 15 amperes. This is 10. That is equal to 1.5. That is equal to 1 by XS saturated per unit. Therefore, excess saturated per unit is equal to how much? XS saturated per unit. Saturated per unit is equal to 1 by SCR. That is equal to 1 by 1.5. How much it is? 0.67. 1 by 5. Correct? 1 by 5 is equal to how much? 1 by 1.5. Okay. Yes. It is 0.67. Am I right? What is your answer? Yes, what's your answer? Yeah. So it is 0.67. Okay. Now, this is about your SCR. So each and every point we have discussed related to SCR. And only the pending is derivation of SCR. I will derive within 5 minutes and so that we will close. Yeah. Let us see derivation of SCR. Lastly, this, yeah. Derivation of SCR. Yes. We know that OCC and SCC, yeah, this is OCC and SCC. IF, E and ISC. This is E and ISC. OCC. This is SCC. SCC. Okay. Yeah. EOC is equal to V rated. This is EOC is equal to V rated. EOC is equal to V rated. Let me call this is IFM. 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 And ISC is equal to IA rated. This is ISC is equal to IA rated. This is ISC. ISC is equal to IA rated. IA rated. Okay. For example, if you take this is point O This is S1. This is S2. S2. But OS1 is equal to IFA. Whereas OS2 is equal to IFM. Fine. So IFM is the field current required to generate rated voltage under open circuit condition. And ISC is the IA rated. Therefore, what is our SCR? SCR is equal to IFM by IFA. Okay. Now, see, from this point, say this is R2, this is R1 point on this SEC. This is Q say, Q. So, yeah. Listen. SCR is equal to, what is SCR? SCR is equal to IFM by IFA. IFM by IFA. IFM is how much? OS2 divided by OS1. That is ISCR. SCR is equal to OS2 by OS1. So I need to find OS2 and OS1. For this, see, from the OCC, let us assume OCC also almost linear. So slope of OCC is equal to QS2. Slope of SCC, QS2 divided by OS2. Correct? Y by X. Slope is equal to Y divided by X. From OCC, slope of OCC, this is vertical height. Y axis QS2, X axis OS2, QS2 by OS2. Okay, QS2 by OS2. Let us take this is M1, OCC, slope of OCC M1, that is equal to QS2 divided by OS1. Similarly, slope of SCC M2 say, M2 is equal to M2 is equal to from SCC is a straight line. This divided by this, no? Yes. R2S2 divided by OS2. Am I correct? This is Y component and this is X component. So, similarly, R1S1 divided by OS1 also correct. Slope can be taken from anywhere. Na? It is a straight line. Slope is same. R2S2 divided by OS2, R1S1 by OS1. So, this is R2S2 divided by OS2 correct. That is also equal to R1S1 by OS1. Both are same. Okay. Yeah. See, this is equation 1. This is equation 2. And this is equation 3. But from equation 2, can I write OS1 is equal to QS2 by M1. QS2 M1. Okay. Say let us, this is 4. And similarly, from 3, can I write OS2 is equal to R2S2 divided by M2. R2S2 divided by M2. Yeah. Similarly, ZS saturated. What is that ZS saturated? ZS saturated is equal to EOC divided by, yesterday I have divided, na? Yes, EOC by ISC IF is at EOC is equal to V rated. Therefore, that is equal to, therefore ZS saturated is equal to what? EOC by ISC. What is EOC? EOC is equal to QS2. QS2 corresponding current is R2S2. R2S2. This is the ZS saturated. Kada. EO2. This is EOC. Okay. And this is R2S2. Where IF is at V rated. Now, V rated means it is related to OS2. So QS2 divided by OS2. That is ZS saturated. And what is ZS base? ZS base is equal to V rated by IA rated. V rated by IA rated. So therefore, ZS is equal to ZS base is equal to what? V rated means QS2 divided by R1S1. R1S1. Okay. R1S1. Now let us substitute all the things in this relation. I hope, do you remember these relations? Fine. Yeah. Now last, by putting these things in OS2 by OS1. So SCR is equal to OS2 by OS1. Yes, OS2 by OS1. But what is OS2? See here, what is OS2? OS2 is equal to R2S2 by M2. R2S2 by M2. R2S2 by M2. Okay. R2 S2 by, is correct. R2 S2 by M2 no? OS2. Next one, OS1 is equal to what? QS2 divided by M1. QS2 divided by M1. Okay. That is equal to what? R2S2 divided by QS2 into M1 by M2. M1 by M2. And that is equal to R2S2 divided by QS2. I can write M1. M1 is equal to what? M1. M1 is equal to QS2 by OS1 again. QS2 by OS1 divided by M2. M2 is equal to M2 is equal to R1S1 by M2 also equal to, from this M2 also equal to what? M2 also equal to M2 is equal to R2S2 by OS2. Okay. Yeah. M2 is equal to R2S2 by OS2 or R1S1 by OS1. R1S1 by OS1. OS1. That is equal to what finally? R2S2 divided by QS2 into QS2 divided by R1S1. So that is equal to R2S2 divided by QS2 into 1 by R1S1 by QS2. What is R2S2? R2S2. R2S2 by QS2 is equal to how much? R2S2 by QS2 is equal to 1 by ZS saturate. that is equal to 1 by ZS saturate, correct, into R2S2 by QS2, 1 by ZS saturate. Okay. That divided by, what is this, QS2 divided by 1 is equal to how much? QS2 divided by R1S1, that is ZS base. Or simply, I can keep this as it is, QS2 divided by, sorry, QS2 divided by R1S1. This is ZS base, na? That is ZS base. This is equal to, once again I will write 1 by ZS saturated divided by again ZS base. Denominator of denominator I am bringing. That is equal to what? 1 by ZS saturated per unit. SCR is equal to. Therefore, SCR is equal to 1 by ZS saturated per unit. That is nearly equal to 1 by XCS saturated per unit. Okay, the derivation. Right? Yeah. So with this, we are completed our topic. SCR along with the derivation also. Because some people will interested, sir, how it is coming, how it is coming. That's the reason I am deriving. At the time of examination, not necessary, no derivation is required. Okay? Yeah. So with this, we are completed our syllabus. Today's class. We will meet in the next class. And any doubts are there, please you can raise. Hello?
Hello, sir.
Yeah.
Sir, that Portier triangle, that when you derived that, that FA means that armature flux?
Armature MMF.
Armature.
Or you can take in terms of IFA. Field current corresponding to armature to compensate. Due to armature reaction, drop takes place. Na? That can be compensated by giving extra FA.
Means
extra main field current equal to FA.
Means it is after means demagnetization.
Yes. To compensate demagnetization, that much extra field MMF is required.
Means
For example, due to armature reaction, some 20 volts is reduced, say. How can you compensate that? Extra field current has to be given, na? Extra field MMF you have to give.
Okay.
That is equal to FA.
Okay. And that FR, sir? Air gap, na?
FR is to, of course, FR is field MMF or field current required to generate air gap voltage, ER. ER means it is including
V plus IXL.
IARA plus IAXL. Okay, RA can be neglected, fine. IARA, IAXL. It is already generated voltage some 400 volts.
Yes.
Plus compensating resistance drop, plus compensating leakage reactance also.
Okay.
That FR, doing that much. And drop of FA is required to compensate armature reaction. So that FR and FA we are adding again vectorially.
Okay.
I have taken lagging power factor left side, leading power factor you can take this side. Lagging power factor shift right side, leading power factor left side.
Okay. And that FT is the total extra amount of that is means added.
Exactly. So that is FT is required, total field current required. So the total generated EMF is E. If you generate total generated EMF E, after going all the drops, you will get V voltage. You want 400 volts, na? For that you need to generate a E. Some 480 volts you have generated, or 490 volts you have generated, say, after going all the drops, you will get the V. So it is reverse approach. I am starting with V. I want this much voltage. So what are the various drops are there? How much MMFs are required? And by taking consideration, finally I am finding total field MMF. For that I am finding E. So if you generate that much voltage, you will get V.
Okay. And sir, it is a drop or lagging load, so it is means already voltage is dropping in all cases.
Yes,
Only
yes, yes.
voltage. So we
Yes.
are in a added means.
Yes, yes. In leading, how to take, see, this here I have taken for lagging, na? For leading, how to take, leading I can take in this way. This is FR, right? FA I can take in this way. FA. Then this is FT. What happened FT? You see leading power factor, it is reduced automatically. Phasor will take place. Leading. This is for leading. This is for lagging, whatever I have taken for lag. Automatically net field current. You have to reduce.
Okay.
Yes.
Okay. Thank you.
Okay.
Sir.
Hello, sir.
Yes.
Sir, just one thing, sir. This regarding what you mentioned in the same from Rother's turn also, sir. You did mention that in order to compensate this armature reaction, we are adding an additional field current, so, and those two field currents are added vectorially.
Yes, exactly.
Sir, so in that case, so the relation between IF and IA is not proportional, sir. Like if you increase 1 ampere of IF, IA will not become 1 ampere or what, sir?
No, proportionality I am taking. See, when IA increases, what happened? Armature flux also increases, na? To compensate that, I am taking extra field current.
Okay, sir.
They're only proportional. And IFA, IF field currents we are taking the components of the field current. IFA related to armature reaction component. That's the reason I have taken for IA lagging, IA leading.
Sir, so the angle between the IF that is main field and the extra current that is to be provided to compensate, this will be the cos inverse of the power factor of the loader.
Yes.
So those two will be added and will get some resultant current. That will be the one we have to inject into field winding to compensate this.
Exactly correct. You are right. Exactly, that's what. But other leading power factor say you have to reduce that. Automatically, the phasor will take place. IFT will be less.
All right, sir.
Correct.
Yes, sir. Thank you, sir.
Right.
Hello, good evening, sir.
Good evening.
Sir, in Portier triangle, we are using the general formula. So second.
Yeah.
Could you open that slide, sir?
Portier triangle.
Second diagram. Next one.
This is clear for you?
This is for lagging load, no, sir. This is clear.
Okay.
In that, sir. Sir, from the D point to the V0 can be taken as armature drop.
Which one?
From point D to E0. That will be armature drop.
Yes. From point
D to E0. Because we are taking from
E0.
From
yes,
E, sir.
No, that is only FT. FT corresponding to E0. FT is corresponding to E0.
Yes, sir.
This is corresponding to E0. Then what is your doubt?
My doubt is the total drop will be excess, no, sir. From OCC ZPF.
Okay. That relation is valid only for ZPF lagging only, correct? This diagram is corresponding to ZPF lagging. Whatever I have drawn, very beginning is there, na? That is related to for ZPF lagging is correct. ZPF, this one, ZPF lagging is, if you say this is for ZPF lagging, exactly I can say it is IAXS. This is E. ZPF lagging, if you find, you will get here only exactly. But I am taking for 0.8 lagging, say. Can you get the same thing?
No.
0.8 lagging. Sir, can you get the same thing? No. You cannot get. This is for, that's the reason IA at an angle 90, XS at an angle 90 only, this arithmetic sum valid. If you take IA at an angle minus 36 point, can you get this? No.
Sir, my doubt is not that, sir. From the point H to D, we are taking IAXL. From point D to E0 can be taken as the IAXL
I'm asking.
This is not correct. That's what I am saying. This is valid for what? ZPF lagging, if you find regulation, you are correct. 0.8 lag,
Sir.
I am making generalization.
Sir, when from which we, how can we take from the armature drop, sir? We are taking the reactance drop, no, sir, leakage reactance. If you want to find the
In this equation,
armature
I have
reaction
added. See, this equation, it will take care about all the things. This is what? Leakage reactance and all that. Now, ZPF lagging, if you see, in this ER, ZPF lagging, if you take, what you will get? V cos phi is equal to how much? 0. IRA 0. Then V sin phi is equal to V plus IA XL. Arithmetic sum you will get.
Okay, sir.
బాబు అర్థమవుతుందా నీకు? ఈఆర్ అనేది జెడ్పిఎఫ్ ల్యాంక్ తీసుకో. జెడ్పిఎఫ్ ల్యాంక్ తీసుకుంటే అప్పుడు ఏమొస్తుంది నీకు? ఈఆర్ ఇస్ ఈక్వల్ టు ఈక్వేషన్ లో వి ప్లస్ ఐఏఎక్స్ఎల్ వస్తుంది. అప్పుడు నేను తీసుకున్న ఫస్ట్ డయాగ్రామ్ అది జెడ్పిఎఫ్ ల్యాంక్ డ్రా చేశాను. ఓకే, బట్ ఇఫ్ ఐ టేక్ 0.8 lagging, that relation Portier triangle as drawn for ZPF lagging. After drawing Portier triangle, FA is same and IAXL is same, but they are added vectorially. This IFT is there, na?
Yes, sir.
That you have to find. That will be different for various power factor. But that FT is equal to, according to ZPF lagging, say, you will get FT is equal to here. Exactly. Whatever you told, that will be the FT will becomes. Where it is FT? Sorry. This FT మీకు ఇక్కడ వస్తుంది ఎగ్జాక్ట్ గా ఈ B కింద వస్తుంది FT. This will become FT. Now this is going to be IAXS exactly you will get.
Okay, sir.
నేను తెలుగు వస్తుంది కదా నీకు? నేను జనరల్
Yes, sir.
ప్రతి పవర్ ఫ్యాక్టర్ కి చేస్తున్నాను, జనరలైజ్ చేస్తున్నాము. ఒకసారి పోర్టియర్ ట్రయాంగిల్ వచ్చిందంటే ఆ BHFA ఏదైతే ఉందో అది తీసుకుంటాను, IAXL తీసుకుంటాను. ఇక్కడ ఈ ఫస్ట్ డయాగ్రామ్ లో ఏం చెప్పాను? మనకి ఎలాగూ పోర్టియర్ ట్రయాంగిల్ వచ్చింది, దాని నుంచి IAXL అండ్ FA. ఆ డయాగ్రామ్, దిస్ డయాగ్రామ్ వీ హ్యావ్ డ్రాన్ ఫర్ ZPF లాగింగ్, మొత్తం ZPFC. ఓకేనా? తర్వాత బై యూజింగ్ దిస్ మెథడ్ I want to find the regulation for 0.8 lagging. అప్పుడు ఎలా చేస్తారు? ఫర్ 0.8 lagging అసలు ఈ పోర్టియర్ ట్రయాంగిల్ వ్యాలిడ్ కాదు. చూడండి ఇక్కడ ఫర్ ఎగ్జాంపుల్ 0.8 lagging, దిస్ ఈస్ ద 0.8 lagging సే, దానికి IAXL ఇక్కడ రాదు, ఇక్కడ వస్తుంది, ఇలా వెళ్తుంది IAXL.
Yes, sir.
వర్టికల్ గా రాదు. ఎట్ దట్ టైమ్ ఫస్ట్ ఆఫ్ ఆల్ పోర్టియర్ ట్రయాంగిల్ is not valid. Portier triangle is valid for ZPF lagging only. That's the reason it is ZPF method. But once after getting Portier triangle, we can find the regulation for any desired load condition. Adi. Andukane ikkada what we are doing here, I am taking for generalization. V cos phi antunnanu. V cos phi means 0.8 lagging aithe 0.8 I will write. 0.6 lagging, 0.6 lagging. So then according to that, we are finding FR. How FR we are finding? From OCC. మనకు ఆ ZPF ఫస్ట్ డయాగ్రామ్ లో FR వచ్చింది చూడండి, అది ఎగ్జాక్ట్ గా ER అంటే రెండు వర్టికల్ గా వచ్చింది. కానీ ఇప్పుడు మీకు పవర్ ఫ్యాక్టర్ మారిస్తే ఏమవుతుందంటే V కి ER కి కొంచెం యాంగిల్ కూడా వస్తుంది.
Yes, sir. Some difference will come. Some phase angle difference will come from that.
ఫేజ్ యాంగిల్ డిఫరెన్స్ వస్తుంది కదా. V ఇట్లా ఉందనుకో, IA ఇక్కడ తీసుకున్నావు, ఓకేనా? ఇది V. ఇప్పుడు ఏమవుతుంది నీకు? IAXL ఎక్కడ వస్తుంది? ఇక్కడ వస్తుంది. ఇది ER అవుతుంది, అప్పుడు ఇది ER ఇలా అవుతుంది, అవునా కదా?
Yes, sir. Delta angle will come in there.
మాకు కొంచెం యాంగిల్ వస్తుంది దాని మధ్యలో, అప్పుడు IAXS వస్తే ఇంకా యాంగిల్ వస్తుంది. నేను ఇంతకుముందు రాసింది ZPF లాగింగ్ కరెక్ట్ గా రెండు అరిథమెటిక్ సమ్ అనేది వ్యాలిడ్ ఫర్ ZPF లాగింగ్.
Okay, sir.
అందుకనేసి నేను తర్వాత జనరలైజేషన్ ఇచ్చాను. ఇదంతా ప్రొసీజర్ ఫర్ జనరలైజేషన్. Okay.
Okay, sir. I got it. Thank you so much, sir.
Okay. Yeah, next. Hello. Yeah. I am unmuting all the people. Please.
Hello, sir.
Hello.
Sir, will you please explain the ZP of a phasor, sir, once again?
ZPF phasor, sir.
Yes, sir. Yes, sir.
Yeah. Which slide? Tell me. This one.
No, sir. Next.
This one.
No, sir. No, sir. Sir, the characteristics you are drawn there, sir. Oh, yes. Yes, sir. This one. This phasor, sir. Left side phasor.
See, this I have taken for ZPF lagging. ZPF lagging means V. This is V, no? This is V. V phasor. This is V phasor. Current lags. Phasors are rotating in which direction? Let us say in counterclockwise direction. Counterclockwise direction. Here IA lags. How much angle? 0 perfect lagging. Because ZPFC for zero lagging. IA have taken ZPF lagging. When this is IA means how IAXL will be perpendicular.
Yes.
Perpendicular means I am adding IAXL. This is ER. ER.
Yes.
Okay. With that ER, I am simply extending onto the OCC. And this is V. This is V. So the height between these two, that is IAXL. IAXL. Okay. IAXL. Now, here again, I am adding FA. Armature flux, FA will be opposite direction exactly. In the armature flux, I want to compensate that armature flux. Due to armature flux, some 2 milliwebers are decreased. I have to increase another 2 milliwebers. So therefore, that's the reason I am taking FA in this direction. The FA, FR should be added. Total field current.
Yes, sir.
So that FT is equal to FR plus FA. But that FT is related to E. E. That FT related to what? E.
Yes,
So
sir.
it is E. Here point I can say it is nothing but E. Here, that is E.
Yes.
This is E. That E related to what? FT.
FT.
And there it is V plus IAXS. V plus IAXS is equal to E.
Yes.
Total FT. Okay.
Sir, this FA and FR, how we have taken in opposite direction means?
FR, FA.
We have taken in opposite direction of I.
Armature reaction, lagging power factor, demagnetization.
Yes, sir.
Demagnetization, for example, this is the armature flux. If this is armature flux means in which direction I need to produce main field flux? Reverse.
Reverse direction to compensate that.
To compensate that.
Okay, sir. And sir, FR is for what you told?
FR is to generate a voltage for ER. FR is the MMF to generate voltage ER. ER means air gap voltage. That includes V plus resistance drop plus leakage reactance drop. If you have given FR, say, it is taking care about all these things. It is maintaining rated voltage, resistance drop also, leakage reactance drop also, it is taking place. And to that FR, armature reaction drop is not considered so far. Therefore, add FA to that FR, then total drops are considered.
Okay, okay, sir.
That's the reason I have added FA plus FR vectorially. This diagram, FR, FA added. Because armature reaction is mainly depends on the power factor. Lagging power factor this side, leading power factor is left side.
Okay, sir.
Then FT, total E. This is for general power factor. First diagram, whatever I have drawn, that is for ZPF lagging only, I have explained. Okay. Now next procedure steps I have explained for any generalized power factor. You can find the regulation for 0.8 lagging also, 0.6 lagging also, leading also. That is the steps I have given.
Okay, okay, sir.
Fine.
Thank you.
Yeah.
Hello, sir.
Hello, tell me.
Sir, in the derivation of SCR, sir, second last slide.
Derivation?
Yes, sir.
Tell me.
Sir, there, that second equation, sir, slope of M1. Sir, that denominator should be OS2, I think.
Where?
Previous slide, sir, previous.
This one?
Sir, this equation 2, slope of M1. Slope of OCC.
Slope of M1. QS2 by OS1 only correct. Y by X, na?
Sir, X is OS2, sir.
Slope Y is equal to M is equal to what, na? Slope is equal to what?
Y
M-
by X, sir.
This is Y is QS2, na?
Yes, sir.
This is X is OS2. Correct.
Yes, sir.
Oh, M1, na? Slope of M1 OS2. You are right. You are right. This is OS2, na? You are
Yes,
saying?
sir. Yes, sir.
R2S2 by this is OS1. Correct. OS1. Okay.
No, sir, that is correct. I think R2S1 is, sir. I think that third equation is correct.
R2S2 by OS2. Third. Yeah. This is
R2S2.
correct. OS2.
Yes, sir, that is correct. Third one is correct. Yes, sir. Yes.
Yeah. Okay. In this way, will it affect anywhere
Okay, sir.
earlier? No, later onwards.
Final answer is coming right, so I think we will be okay.
Okay. In between it is by. Yeah.
Yes.
Final answer is correct only.
Okay, sir. Thank
OS2
you.
is equal to R2S2 by
Yes, sir.
R2S2 by M2. That is correct only, na? R2S2 by slope. In place of M1, I have substituted correct, yeah? M1. M1 is equal to QS2 by OS1, I have substituted.
Q by OS2.
OS2,
Yes, sir.
yeah? OS2, I think.
Yes, sir.
This is OS2. R1S1 by M2 is equal to what? M2 is equal to R2S2 by OS2. Is R1S1 by
That is
OS1?
correct, yes, sir. Yes, sir.
Yeah. QS2 by. Yeah.
Sir, then that will not get cancelled, sir.
Okay.
OS2 and OS1.
Just a minute. Let me check out. Yeah, it will come somewhere. Okay, just a minute. See, SCR is equal to OS2 by OS1. Slope of OCC M1 is equal to how much? M1 is equal to QS2 by OS2. Right? Yeah. QS2 by OS2. OS2. Slope of M2 is equal to SCC. R2S2 by OS2, correct? R1S1 by OS1, correct? And from 2, OS1 is equal to what? QS2 by OS2, it is, no?
Yes, sir.
OS2 is equal to QS2 by M1. Yes. And OS1 is equal to, from this, OS1 is equal to R1S1 by M2. R1S1 by M2. R1S1 by M2. Okay. Z is saturated. Z is saturated is equal to what? Z is saturated is equal to QS2 divided by R2S2. Correct. ZS base is V rated by QS2 divided by R1S1. Correct only. Yes. Now let us see. OS2 by OS1. OS2 by OS1. What is OS2? R2S2 by OS2 is equal to QS2 by M1. QS2 by M1. Just a minute. Let us do this again. Just a minute. Okay. See OS2. OS2 is equal to what? QS2 by M1. Correct? QS2 by M1 divided by what is OS1? OS1. R1S1 by M2. R1S1 by M2. that is equal to QS2 divided by R1S1 into M2 by M1. Okay. Yes. So QS2 divided by R1S1 into M2. What is M2? See, M2. M2 is equal to R2S2 by OS2. R2S2 by OS2 I am writing, divided by M1 is how much? M1. QS2 by OS2. OS2. Okay, yes. And that is equal to QS2 divided by R1S1 into R2S2 by QS2. That is equal to, what is QS2 by R2S2 is equal to QS2 by R1S1. That is ZS base, correct? This is ZS base. So R2S2 by QS2, R2S2 by QS2. Yeah, that is equal to, let me take, this is QS2 divided by R2S2. Okay, that is ZS base into, what is QS2 by RPS2? QS2 by RPS2 is ZS saturate. ZS saturate. This is equal to 1 by ZS saturate divided by ZS base. That is equal to 1 by ZS saturated per unit. Correct? Huh? Hello?
Yes, sir. Yes, sir. Yes,
Yes.
sir.
Yes, you are correct. But finally, we got answer also correct. I don't know where we
Same. Yes, sir.
are.
Yes,
Right,
sir.
right. Good, good.
Thank you, sir.
Right, good. Very good. Good observation. Yeah. Okay. I'm closing the session. Right.